Ever find yourself dozing off when someone mentions statistics? You're not alone. But what if I told you that statistics isn't just about dusty formulas and endless spreadsheets? It's actually the secret sauce behind everything from predicting the next viral TikTok trend to figuring out why your favorite coffee shop always seems to run out of oat milk on Mondays. So wherever you are, relax, get comfortable, and let's dive into 2.7 hours of soothing statistics to help you drift off to sleep. Don't worry. Unlike your high school math class, there won't be a quiz at the end. Now let us begin. Descriptive Statistics. Descriptive statistics revolve around summarizing data so that complex sets of numbers become easier to interpret. Rather than sifting through hundreds or thousands of points, analysts want a few convenient values that capture important characteristics. 3 key measures, mean, median, and mode, provide different glimpses into what might be considered the typical or central point. Although they are collectively referred to as measures of central tendency, each one distills information in a unique way and can influence how results are interpreted or misinterpreted. At the simplest level, the mean is what most people know as the average. It is calculated by adding every value in a data set and then dividing by the total number of observations. Because each data point contributes equally, unusually large or small values can pull the mean higher or lower, making it a sensitive measure of central location. In a purely symmetrical distribution with no extreme outliers, the mean can represent an accurate portrait of the data's overall position on the number line. In contrast, the median is the middle value once data are sorted from smallest to largest. For an odd number of observations, it is the single central point. For an even number, it is the average of the 2 central points. Because it only depends on the order, not the magnitude, the median stays steadier when extreme values appear. Suppose you have salaries in a company. One exceptionally high executive salary could inflate the mean, but the median would remain relatively unaffected by that single outlier. The mode, often overlooked, is the most frequently occurring value in a data set. While it may not always seem intuitive for numerical data, it can be extremely informative for categorical information or distributions with multiple peaks. If you have a data set of test scores and a certain score repeats itself more than any other, that value becomes the mode. In some distributions, there may be no clear single mode, and in others, multiple modes might exist, each reflecting different clusters in the data. Although these 3 measures are commonly grouped together, each tells a separate story about the data. The mean captures an overall average, the median focuses on the central rank, and the mode highlights popularity. By comparing them, one can glean insights about the shape of the distribution. If the mean is greater than the median, there may be a right skew, suggesting a tail stretching into larger values. Conversely, if the mean is less, that often signals a left-skewed distribution with lower outliers. Outliers in particular pose unique challenges to these measures. A single data point far from the rest can drastically alter the mean, while leaving the median mostly untouched. The mode may or may not remain relevant, depending on how repeated that outlier value is. In real-world contexts, such as household income or property values, a few extremely large observations can skew the mean significantly. Understanding whether to report the median or the mean can thus become an important decision in policy, research, or business. In addition to these core statistics, descriptive analysis also encompasses ways to measure spread, such as range or standard deviation, but the focus on central tendency remains crucial. When presenting findings, many reports highlight one or more of these measures to offer a compact depiction of overall level. Sometimes graphs or tables accompany the numerical values. For instance, a histogram might reveal how the data cluster around the mean, or if multiple peaks suggest more than one mode. Summaries become more powerful with visuals. Practical applications abound, from teachers analyzing test scores to executives reviewing quarterly sales. The choice between mean and median can shift interpretations in fields like real estate, where a few mansions might inflate the average house price. Professionals also consider whether to highlight the mode, particularly in inventory management, where the most common item size or color might be extremely relevant. By considering how data concentrate around certain values, these measures can guide staffing decisions, pricing strategies, or resource allocation across many sectors. Despite their simplicity, problems can arise when these measures are selected without context. If a data set is heavily skewed, the mean might paint an unrealistic picture. If a distribution contains multiple clusters, reporting a single median could obscure important subgroups. Even the mode might mislead when a data set has many values tied for frequency. Thus, a thorough descriptive analysis will often present several of these summaries simultaneously, augmented by additional checks that delve deeper into the underlying patterns shaping the data. Interpreting descriptive statistics benefits from understanding the domain. A sports analyst might care about the mean points per game for a particular athlete, but might also watch for whether that average hides significant fluctuation game to game. The median time spent on a website might be more informative than the mean, if there are occasional users who linger for hours. The mode might best capture typical sizes in clothing inventory. Recognizing the differences in proper contexts for each measure is fundamental to clear communication. Presentation also matters. If you've got a table of age data, specifying the mean, median, and mode together can illuminate whether the sample is primarily young adults or older individuals. Visual representations like bar charts, box plots, or histograms can support the numerical summaries and highlight skew, outliers, and possible bimodal shapes. In routine professional settings, stakeholders might only look at a simple average or quartiles, so it's crucial to choose the measure that best reflects the story you want to convey. Another subtlety is how data are collected. If the sample is biased or incomplete, even the best measure of central tendency might give a distorted portrayal. Gathering robust data involves rigorous methods that avoid convenient sampling or flawed instruments. Sometimes the issue lies in misreported values, especially in sensitive topics like income. In those cases, verifying correctness is essential to produce reliable descriptive statistics. Once the data are trustworthy, mean, median, and mode become powerful tools for summarizing large volumes of information. Inferential statistics. This process starts with the assumption that the sample has been selected or gathered in such a way that it faithfully represents the broader group's attributes. By analyzing measurements, responses, or observations from that smaller set, statisticians hope to reason about the entire population's parameters, such as its average income or the proportion of individuals favoring a certain policy. While descriptive statistics concerns itself only with summarizing the current data, inferential statistics takes a significant step further by asking what those observed patterns imply for unobserved individuals or future outcomes. Choosing a sample to mirror the population is both an art and a science. Ideally, one wants a random selection process so that every member of the population stands an equal chance of inclusion. Although practical constraints may force compromises, like convenience sampling at a local venue, such shortcuts can degrade how representative the final sample is. Stratification, cluster sampling, and systematic sampling are all techniques devised to improve coverage of different subgroups, especially when the population is large or diverse. Once the data have been properly collected, the next challenge lies in translating these raw numbers into statements about the population's unknown parameters. One important concept in inferential statistics is the difference between a parameter and a statistic. A parameter refers to a numerical characteristic of the entire population, such as the true mean score on a standardized test for all students in a district. Because it is often impractical to measure every single individual, we do not know this parameter with certainty. Instead, we derive a statistic from the sample, like the sample mean, which approximates that unknown figure. If we picked a different subset of the population, we would likely get a slightly different sample mean. This variability from sample to sample underpins a major theme in inferential statistics: accounting for sampling error. Central to understanding this variability is the idea of the sampling distribution. Imagine collecting many samples from the same population and computing the mean each time. Plotting all those means would produce a distribution describing how the sample mean behaves across repeated draws. The central limit theorem, a powerful result in statistics, states that when samples are sufficiently large, this distribution of sample means tends to a normal shape, even if the original data themselves are not normally distributed. The theorem's significance lies in its ability to justify the use of normal-based confidence intervals and hypothesis tests in numerous scenarios where the sample size is big enough to mitigate irregularities. Confidence intervals are a hallmark of inferential practice. Instead of pinpointing a single number as the population mean, analysts present an interval that they believe contains that unknown parameter. For instance, a 95% confidence interval suggests that if the same sampling procedure were repeated many times, about 95% of those constructed intervals would capture the true parameter. Formally, it is not correct to say there is a 95% chance that the parameter lies within the interval for a single experiment, because the parameter is presumably fixed. Yet, in everyday language, confidence intervals are treated as plausible ranges that reflect uncertainty. Narrow intervals indicate more precision, often the result of larger sample sizes or smaller variability in the data. Hypothesis testing provides another backbone for inferential conclusions. Instead of trying to estimate a parameter outright, this approach begins with a tentative statement known as the null hypothesis. This might be that a new medicine has no effect compared to a placebo, or that there is no difference between two groups on a certain measure. Then, researchers specify an alternative hypothesis, which proposes that there is indeed an effect or a difference. By analyzing how likely the observed data, or data more extreme, are under the null hypothesis, statisticians arrive at a p-value. If that value is sufficiently low, commonly below the conventional threshold of 0.05, it is deemed that the data are incompatible with the null assumption, and it gets rejected in favor of the alternative claim. This procedure, while widely used, carries its own pitfalls. Misinterpretations abound when p-values are taken as direct measures of whether a hypothesis is true or not. The p-value instead quantifies how surprising the data would be if the null scenario held. Moreover, the choice of significance level, typically 5%, is arbitrary and may lead to paradoxical results across multiple studies. Type I errors occur when a true null hypothesis is wrongly rejected, while type II errors arise when the data are not sufficiently compelling to reject a false null hypothesis. Balancing these error risks involves selecting appropriate sample sizes and adjusting significance levels. Inferential statistics also extends to regression analysis, where the primary goal is to deduce relationships between variables within a population. Parameters such as regression coefficients are estimated from sample data, and analysts use t-tests or f-tests to check whether those estimated relationships are statistically significant. Models that appear to fit well in one sample may not generalize to others if the original subset was too narrow or introduced biases. Regularization, cross-validation, and replication studies can help confirm that these findings are not mere artifacts of a particular data set. Real-world applications for inferential statistics range widely. Polling organizations leverage it to forecast election results, contacting a fraction of the voting population to estimate each candidate's support and margin of error. Pharmaceutical trials evaluate how well a new treatment might perform if given to the entire patient group. Economists analyze consumer surveys to anticipate future spending patterns, while ecologists track animal populations without having to tag every individual. The unifying theme is to transform limited observations into claims that have broader applicability, always accompanied by an estimate of uncertainty. Though confidence intervals and p-values are the most visible faces of inference, Bayesian methods offer an alternative perspective. Instead of just focusing on frequencies and repeated sampling, Bayesian analysts incorporate prior beliefs about parameters and update those beliefs in light of the new evidence. This framework yields a posterior distribution, which reflects the probability of different parameter values after considering both prior knowledge and observed data. In practice, Bayesian approaches can handle complex models with greater flexibility, but they require careful consideration of how priors are chosen, since subjective judgments can enter the analysis. Inferential statistics ultimately boils down to systematic reasoning about uncertainty. It clarifies how likely it is that a sample-based conclusion could be wrong, enabling researchers to weigh evidence responsibly. By quantifying confidence levels or p-values, the discipline highlights the limitations of our data rather than ignoring them. Interpreting results in a context-dependent manner remains crucial. An apparently large effect size might be unimportant in a medical study if the risk of harm is high, just as a borderline p-value might still guide important policy decisions if lives hang in the balance. Regardless of the specific methods chosen, the inferential mindset asks, how can we extend findings beyond the sample we've tested? That question compels rigorous planning for data collection, conscientious checks of assumptions, and transparent reporting of margins of error. When done correctly, inferential statistics becomes a powerful engine for discovering patterns, testing theories, and making informed choices in a world where complete certainty is unattainable, but well-reasoned approximations lead us forward. Regression analysis. Regression analysis stands as one of the core methods in modern statistics and data science, serving to uncover how a target variable shifts in response to changes in one or more explanatory variables. By fitting an equation that links predictors to an outcome, researchers and professionals gain a systematic way to forecast trends, test theories, and guide practical decisions. The fundamental premise is that patterns observed in historical data can be generalized to explain or predict future observations, provided the model is well specified and the context remains consistent. Traditional linear regression forms the bedrock, but other variations like logistic, polynomial, or ridge regression expand its versatility to handle classification tasks, curvature, or regularization. At its most basic level, simple linear regression examines the relationship between one independent variable and one dependent variable. If a biologist wants to see how plant growth varies with hours of sunlight, each data point might represent a single plant's observed height alongside the daily sunlight it received. Fitting a line through these points in a way that minimizes the sum of squared deviations from the observed values yields coefficients that quantify the slope and intercept of this best fit line. Interpreting that slope provides insight into how many units of growth one might expect for each additional hour of sunlight. While this approach can be powerful, it also imposes assumptions such as linearity between the variables and normally distributed residuals. In everyday business contexts, multiple regression comes into play. A company analyzing sales trends might consider advertising budget, product price, seasonal factors, and competition as independent variables. Each explanatory variable gets its own coefficient in the resulting equation, showing how holding one factor constant while changing another by a single unit affects predicted sales. This arrangement highlights the fact that real-life outcomes seldom hinge on a single cause. The interplay among predictors can be complex, and carefully parsing these relationships helps clarify which levers most strongly influence results. But regression is not purely about linear relationships. Polynomial regression, for instance, allows for curves, capturing more nuanced trends such as diminishing returns or rapid growth, followed by plateaus. By introducing squared or higher-order terms, the model can adapt to curvature in the data. Interactions can also be considered, where the effect of one predictor changes depending on the level of another. This might be relevant if advertising only boosts sales significantly when prices fall within a certain range, revealing that real-world dynamics often resist an oversimplified, purely linear explanation. Logistic regression, despite the name, is used primarily for classification problems. Instead of modeling a continuous outcome, logistic regression predicts the probability of belonging to one category or another. In medical research, it might evaluate whether a patient is likely to develop a condition based on risk factors. The model yields odds ratios, a measure of how the likelihood of a particular outcome shifts when a predictor changes. Though the mechanics differ from standard linear regression, logistic employs the logistic function rather than a straight line. The idea of relating variables through estimated coefficients remains much the same. Choosing the right regression variant also involves diagnostic checks to ensure model validity. Residual analysis is paramount. After fitting the model, one inspects residuals, the differences between predicted and actual values, for patterns. If those residuals show a non-random structure, like consistently rising or falling as the predictions grow, that may signal violations of linearity or heteroscedasticity, where the error variance changes with the magnitude of the outcome. In such cases, a transformation of the data, a different model specification, or more advanced techniques may be warranted. Multicollinearity poses another issue. When multiple predictors correlate strongly with each other, it becomes difficult to disentangle their individual effects. The model's coefficients may blow up in magnitude or flip in sign, leading to confusion about which variables truly matter. Techniques like variance inflation factor, VIF, measurements help detect and mitigate this problem. Sometimes domain expertise can guide which variable to keep or how to combine correlated predictors, ensuring the final model remains interpretable and stable. Regularization methods, including ridge and lasso regression, provide additional strategies for dealing with multicollinearity or high-dimensional data. By imposing a penalty on the absolute or squared sizes of coefficients, these methods shrink parameter estimates, preventing overfitting and improving the model's capacity to generalize to unseen data. In fields like genomics, where the number of potential predictors can dwarf the sample size, these penalized techniques ensure that a meaningful subset of variables emerges without trying to fit each predictor too precisely. No matter the variant, one must remain cautious about causal claims. Regression analysis can reveal strong relationships, but correlation does not guarantee a direct cause and effect link. Omitted variable bias arises when a hidden factor influences both the dependent variable and the predictors, artificially inflating or suppressing observed associations. Randomized experiments, instrumental variables, or longitudinal designs might be necessary to assert that one factor truly drives another. Nonetheless, even without proving causality, regression can guide predictions and highlight fruitful lines of further inquiry. Practical deployment of regression models has expanded with the availability of computing resources. From basic spreadsheet tools to advanced software libraries in Python or R, building, validating, and refining regression models no longer requires manual calculation. Automation can speed up workflows but can also lead to black box outcomes if users fail to scrutinize assumptions and interpret results responsibly. Visualization techniques, such as plotting predicted lines against observed data or mapping out partial dependence, help expose hidden issues and communicate results effectively to non-technical audiences. In forecasting scenarios, regression provides a transparent method for projecting trends into the future. For example, An energy provider might use historical consumption, weather data, and regional growth indicators to estimate next year's demand. By continuously updating the model with new observations, they can refine predictions and adjust infrastructure or pricing strategies accordingly. That said, unforeseen events, economic shocks, policy changes, technological breakthroughs can disrupt established patterns, so the reliability of regression-based forecasts can vary over time. In academic research, regression serves to test theoretical models by checking whether empirical evidence aligns with hypothesized relationships. Economists might propose that consumer spending correlates with disposable income in a certain pattern, then gather panel data to estimate the relevant coefficients. If the results align with theoretical predictions, it adds credibility. If not, the discrepancy may suggest that the theory is incomplete, or that unmeasured variables are at play. In this way, regression acts as a feedback mechanism for revising both practical strategies and conceptual frameworks. Despite its ubiquity, regression analysis demands thoughtful application. Even a well-fitted model can fail if the data are biased or insufficient. For instance, historical loan approvals might underrepresent certain demographics due to discriminatory practices, causing the model to perpetuate bias. Ensuring data quality, acknowledging limitations, and periodically re-evaluating outcomes is essential. An overemphasis on statistical significance or high R-squared values can also be misleading. Context, effect size, and domain insights matter just as much as neat statistical metrics. Ultimately, regression analysis empowers analysts to extract structured insights from swirling masses of data, pinpointing how multiple factors converge to shape outcomes. By expressing relationships in a concise equation, the technique delivers both predictive power and interpretive clarity, assuming the underlying assumptions are not flagrantly violated. Organizations rely on these methods to inform everything from marketing campaigns to public policy, while scientists embrace them to validate theories or unearth new patterns. In a world brimming with information, regression stands as a versatile lens that brings clarity and direction, illuminating how changes in one variable resonate through the complex system at large. Central tendency. Central tendency refers to the idea of identifying a single representative value in a data set, offering a snapshot of its overall level or typical point. While it may seem straightforward to choose one number to summarize an entire collection of measurements, there are actually multiple ways to define what is central. 3 measures, mean, median, and mode, each tackle this question from a slightly different angle. Though simple in concept, these metrics have profound implications in everything from everyday decision-making to rigorous scientific analyses, making them indispensable to anyone who wants to navigate the sea of data that swirls through modern life. The mean is generally the first measure that comes to mind when people think about averages. Calculated by summing all the values and dividing by the total count, it provides a single figure around which the data might cluster. Because every data point contributes directly to the sum, the mean encapsulates the overall magnitude of the data set. In contexts like physics or engineering, where measured values tend to fluctuate around an equilibrium, the mean can be particularly illuminating. It captures the combined weight of all observations, essentially acting as a balance point on the number line. However, the power of the mean comes with a downside. It is highly sensitive to extreme values. A handful of extraordinarily large or small points, sometimes termed outliers, can pull the mean far from the majority of the data. This effect can be beneficial if those extremes are legitimate observations that reflect critical real-world phenomena, such as large-scale transactions in an economic analysis. On the other hand, if outliers arise from measurement errors or data entry mistakes, relying solely on the mean might paint a distorted picture. Knowing how and why the mean shifts is essential for interpreting results responsibly. Where the mean can be skewed by extremes, the median stands as a more robust alternative. The median is the exact midpoint once the data are arranged in ascending or descending order. If there is an odd number of points, it is the single middle value. If there is an even number, it is the average of the two central values. Because this calculation depends only on position rather than magnitude, it retains stability in the face of outliers. When summarizing skewed data like household incomes, the median frequently delivers a more typical figure than the mean, which might be inflated by a few very wealthy individuals. Even so, the median has its own limitations. It ignores any nuances beyond whether a point lies to the left or the right of the central rank. Although that makes it resistant to distortion, it also sacrifices the finer details that the mean reflects. In everyday contexts like real estate, where home prices can vary dramatically, observers often benefit from comparing both mean and median. If the two measures lie close together, the distribution might be fairly symmetrical. If they differ widely, it hints at a skew. Policymakers might look to the median for a clearer sense of what is truly normal for the bulk of the population, especially when wealth or property values are unevenly distributed. Alongside mean and median, the mode may at first glance seem less relevant, especially for continuous data. Defined as the most frequently occurring value within a data set, the mode often shines in categorical scenarios. If a clothing retailer wants to know which shirt size sells most, the mode is the direct answer. In a survey where respondents pick their favorite movie genre, the mode reveals the preference that appears most often, acting as a direct measure of popularity. Even in numerical data, such as discrete counts of daily website visitors, the mode can provide insight into common traffic levels. Some distributions exhibit multiple peaks, leading to more than one mode, bimodal or multimodal patterns. This feature can suggest that the dataset actually comprises several subgroups with distinct centers. Consider a scenario where test scores from two different sections of a class are combined into one dataset. If one group consistently scores higher than the other, the final distribution may have two distinct modes. Recognizing that nuance prevents the oversimplification that can occur by looking at a single average, when data analysts describe their findings, choosing which measure of central tendency to present is not merely a technical detail. The choice often shapes the narrative around the dataset. A charity might highlight the median donation to show that typical contributions come from ordinary donors, whereas a mean-based depiction could be skewed by one extremely generous benefactor. Similarly, a technology company might focus on the mean download time for its app if the distribution of times is fairly symmetrical. However, if many users experience quick downloads while a few face major delays, the median might better reflect the general user's experience. Communicating results ethically and accurately depends on a solid grasp of how these measures function. The trio of mean, median, and mode also plays a critical role in detecting data issues. If the mean, median, and mode are closely aligned, one might suspect a fairly symmetrical distribution. By contrast, if these figures diverge, it raises questions about skew, possible errors, or genuinely interesting structure in the data. Graphical tools like histograms or box plots can then flesh out the story, revealing whether one side of the distribution extends further than the other. The central tendency measures become signposts, steering further investigation where needed. There is as well the practical matter of computing these measures efficiently. Modern computers can calculate mean, median, and mode in a blink. But historically, researchers had to perform these operations by hand. That legacy is reflected in everyday arithmetic. People often default to the mean because it is straightforward to add up numbers and divide, even with just a pencil and paper. Nonetheless, the computational ease does not always make the mean the most appropriate choice, and the same caution applies to using automated software. the availability of quick calculations should not overshadow careful thinking about which measure best suits the data's nature. Context always matters. In fields such as education, the median test score can highlight the point at which half the students scored below and half scored above, signaling how many students meet a certain competency threshold. Meanwhile, in industrial quality control, the mean can track deviations from a target performance level, with any large shift prompting immediate inspection. Similarly, for inventory purposes, the mode might guide purchasing decisions if a single item size repeatedly sells out. These three measures work in tandem with other descriptive tools, such as range or standard deviation, to paint a fuller picture of what a dataset looks like. Yet they remain pivotal in their own right, largely because of how intuitive they are. Mean, median, and mode speak directly to our concept of what is typical. While standard deviation quantifies spread and shape, measures of central tendency anchor us to a reference point. Interpreting them correctly is a hallmark of statistical literacy and a gateway to clearer, more responsible analytics in every domain. In sum, the importance of mean, median, and mode cannot be overstated. Each measure provides a different lens on the data's center, and together they equip analysts, policymakers, students, and everyday consumers of information with a firm foundation for understanding complex results. The mean condenses total magnitude into a single figure, the median resists extremes and locates the middle rank, and the mode reveals the most frequent result. Deciding which one best fits a particular context requires more than just computation. It calls for a nuanced appreciation of distribution shapes, sampling methods, and real-world consequences. That careful reflection separates cursory number crunching from meaningful insight, ensuring that central tendency measures truly illuminate the patterns within our data rather than obscuring them. Hypothesis testing. Imagine you're a researcher testing a new medication you believe could reduce the duration of a certain illness. You gather volunteers, split them into two groups, and administer the drug to one while giving a placebo to the other. After a predetermined period, you measure how many days it took each participant to recover. The data looks promising, but how do you decide, with some measure of certainty, whether your medication truly works better than a placebo? That's where hypothesis testing steps in, transforming raw observations into evidence that can either support or refute your initial assumption. Formal hypothesis testing begins by defining two competing statements: the null hypothesis and the alternative hypothesis. The null hypothesis typically represents the status quo. Your medication has no effect, or there's no difference between groups. In this scenario, the null might state that the new drug does not alter recovery times compared to the placebo. The alternative hypothesis, on the other hand, is what you aim to demonstrate. It proposes that the medication has a real impact, perhaps by reducing the average recovery period. Putting these statements in place creates a structured environment to evaluate the evidence collected from your sample. While the idea sounds simple, the underlying logic involves carefully controlling for the possibility of drawing incorrect conclusions. Hypothesis testing operates under the assumption that the null hypothesis is true until there's enough evidence to reject it. In practice, researchers gather data, like the average recovery time for the treatment group versus the control group, and compute a test statistic. This statistic indicates how far the observed difference deviates from what would be expected under the null scenario. If the medication truly has no effect, you'd expect the treatment and placebo groups to exhibit roughly similar results, subject to random variation. The probability of seeing differences at least as large as what you observed, if the null hypothesis is accurate, is encapsulated in the p-value. A small p-value signals that the observed results are unlikely to have arisen purely by chance, under the assumption of no effect. Standard practice in many fields is to deem a result statistically significant if its p-value is lower than a predefined cutoff, often 0.05. If your test yields a p-value of 0.01, that suggests there is only a 1% chance of getting data this extreme or more extreme if the null hypothesis holds true. In other words, it becomes increasingly plausible that the drug has an actual impact rather than random fluctuation explaining the difference. However, a low p-value doesn't automatically guarantee a miraculous treatment. It simply indicates the improbability of your observed data if no difference truly existed. Researchers must consider a variety of other factors. Sample size, for example, exerts a profound influence. With very large samples, minuscule deviations from the null hypothesis might become statistically significant without being practically relevant. Conversely, small samples can fail to detect real effects. Statistical significance thus provides a threshold, but context and domain knowledge are key to interpreting results meaningfully. Another important concept within hypothesis testing is the risk of error. A type 1 error occurs if you reject the null hypothesis, even though it is actually true. In a medical trial context, that would mean concluding the drug works when, in reality, it does not offer a genuine benefit. The significance level, often 5%, effectively sets the probability threshold for making this mistake. A type 2 error is the opposite. Failing to reject the null hypothesis even though it is false, you would claim there's no compelling evidence of a treatment effect when the medication does indeed have a real impact. The probability of making a type 2 error relates to statistical power, which is strengthened by larger sample sizes, well-designed studies, and effect sizes that are easier to detect. In practice, researchers use various tests depending on the type of data and assumptions about distribution. If you are comparing the means of two groups with normally distributed data, a t-test is common. Should the population standard deviation be known and the sample large, a z-test might be appropriate. More complex scenarios like multiple groups or repeated measurements call for tests such as ANOVA or repeated measures designs. Each test has assumptions about randomness, independence, and distribution shape, emphasizing the importance of careful design and planning before data collection even begins. One crucial aspect is the difference between statistical significance and practical significance. Suppose your medication reduces average recovery time from 10 days to 9.5 days, and you run a large enough trial so that the p-value falls below 0.05. Statistically, you might feel confident in rejecting the null hypothesis. From a practical standpoint, however, a half-day improvement might not justify production costs, side effects, or the necessary shift in medical guidelines. Hypothesis testing doesn't answer whether the magnitude of the effect is important. It only identifies whether it is unlikely to be zero. Interpreting effect sizes and confidence intervals can help determine if an observed difference is meaningful beyond the confines of statistical criteria. Replication stands as another pillar in hypothesis testing. One study, particularly if small, can produce false positives due to random chance, data quirks, or unrecognized biases. Repeating the experiment under similar conditions and consistently observing a low p-value adds credibility to the conclusion. In fields such as psychology or biomedical research, replication crises have arisen because many findings failed to replicate. This underscores that no single test result is the final word. A robust scientific claim emerges from multiple lines of evidence converging. Hypothesis testing also appears outside strictly controlled experiments. Pollsters measure public opinion by sampling a fraction of the population, then use hypothesis tests to infer whether a candidate leads or if two candidates are effectively tied. Quality control engineers at factories analyze defective rates, testing whether recent production runs are meeting company standards. Even financial analysts use hypothesis testing on stock market data to see if certain strategies yield returns significantly above random fluctuations. Across all these domains, the essence remains the same. A structured comparison of observed data against the expectations laid out under a null scenario, yet hypothesis testing remains prone to misinterpretation, especially in popular media. Headlines often trumpet results that were proven by a p-value falling below 0.05, ignoring context, effect size, and the possibility of error or bias. Instead of seeing hypothesis testing as a guarantee, it's wiser to treat it as a tool for gauging how surprising the data would be if there were no genuine effect. Researchers who understand these nuances tend to discuss findings in terms of evidence strength, margins of error, and the bounds of their analyses. While hypothesis testing can powerfully distinguish between random noise and genuine signals, it does rely on the initial framing of the null and alternative hypotheses, the chosen significance level, and the quality of the data collected. A poorly worded hypothesis, a flawed sampling method, or an unaccounted-for confounder can spoil the process from the start. That's why designing experiments or surveys is as important as the statistics that follow. Randomization, blinding, and clearly defining outcomes help ensure that data reflect reality rather than hidden biases. In short, hypothesis testing provides a rigorous framework for deciding whether observed results warrant rejecting an assumption of no difference or no effect. By calculating how likely the data would be if that assumption were correct, it delivers a tool for clarifying when an observed phenomenon is plausibly real. However, it can't prove anything with absolute certainty, and it doesn't replace good judgment or replication. Rather, it forms one vital component of the scientific method, guiding investigators from hunches to evidence-based conclusions, all in a world where uncertainty is ever present but can be systematically examined. Probability distributions. Take a bag of dice and give them a roll, letting those cubes tumble across the table with unpredictable spins and bounces. On the surface, each die's outcome appears governed by luck alone. But beneath that veneer of chaos lies a consistent pattern. Probability distributions capture these patterns, giving structure to what might otherwise seem arbitrary. By defining how likely each potential result is, these mathematical functions allow us to study, predict, and make decisions under conditions of uncertainty. While we can't know for sure which face a die will show on a single throw, we do know that over many throws, the outcomes follow a precise distribution. A probability distribution starts with the concept of a random variable, which is simply a way of assigning numerical values to different outcomes of a random process. For instance, the roll of a fair six-sided die can be represented by a random variable x that takes one of the values 1 through 6 with equal probability. Across thousands of rolls, each face will appear roughly 1/6 of the time. This principle extends well beyond dice. Random variables describe everything from the number of emails arriving in your inbox per hour to the speeds of cars traveling on a highway. The magic of probability distributions is that they offer tools to quantify and analyze these phenomena. Probability distributions fall into two broad categories: discrete and continuous. Discrete distributions describe variables that can take on separate, countable values, like the number of heads in a series of coin flips or the total goals scored in a soccer match. Continuous distributions, on the other hand, describe outcomes that vary along a continuum, such as heights of individuals in a population or the time between lightning strikes. The distinction matters when calculating probabilities. For discrete random variables, you can sum the probabilities of individual values, while for continuous random variables, you integrate a probability density function over a given interval. One of the most iconic examples of a continuous distribution is the normal distribution, often called the bell curve. The term bell curve springs from its shape, which peaks at the mean and tapers symmetrically on either side. Many natural phenomena, such as measurement errors in physics or people's IQ scores, tend to cluster around this familiar curve. Though real datasets rarely match the normal distribution perfectly, the central limit theorem explains why so many things approximate it when averaged over large samples. This theorem states that if you sum many independent random variables, their mean tends toward a normal distribution, no matter the original distributions. This result is why the normal model appears so frequently in statistics. For discrete variables, the binomial distribution stands out as a keystone example. It describes the number of successes in a fixed number of independent trials, where each trial has only two possible outcomes, success or failure. Think of flipping a coin 10 times and counting how often heads comes up. If the coin is fair, the most likely number of heads is 5, but other results can occur as well, each with a calculable probability. By adjusting the probability of success, the binomial distribution adapts to diverse scenarios, from manufacturing defect rates in a batch of products to the likelihood of answering multiple-choice questions correctly. When dealing with events that occur randomly over time or space, the Poisson distribution proves indispensable. Named after the French mathematician Siméon Denis Poisson, it models situations where occurrences happen independently at a certain average rate. If you track the number of calls a help desk receives every hour, the Poisson distribution could predict the probability of getting 5 calls in the next hour, 10 in the following hour, and so on. Because it captures rare events over intervals, it also surfaces in fields like astrophysics, counting cosmic rays hitting a detector, and epidemiology, counting new disease cases in a region. Other distributions fill out the probabilistic landscape. The uniform distribution, for example, assigns the same likelihood to every point in a specified interval. If you pick a random number between 0 and 1, it has an equal chance of landing anywhere within that range. The exponential distribution models the waiting time between independent events, such as a queue forming at a checkout line, and it exhibits the memoryless property. The probability of waiting an additional amount of time is always the same, regardless of how long you've already waited. The variety of distributions available reflects the incredible diversity of real-life processes, enabling statisticians to select or design a function that fits observed patterns with reasonable precision. Each distribution has parameters that control its shape and position. In the normal distribution, the mean determines where the peak lies, and the standard deviation dictates how spread out the curve is. For the binomial distribution, the parameters are the number of trials and the probability of success, while the Poisson distribution depends on the average rate of occurrences in a given interval. By adjusting these parameters, one tailors the theoretical model to the observed data. Analyzing how parameter changes affect the distribution helps us understand the underlying process, whether that process involves customer arrivals or rainfall totals. Real-world applications of probability distributions abound. In finance, traders model stock prices or returns using distributions that capture fat tails, reflecting the chance of extreme market swings. Meteorologists use distributions to forecast rainfall levels or temperature ranges, providing probabilities for flooding or heat waves. Engineers might rely on the exponential or Weibull distributions to model product lifetimes, thereby estimating failure rates and scheduling preventive maintenance. Health researchers examine distributions of patient recovery times to gauge the effectiveness of treatments, while marketing analysts estimate the distribution of purchasing frequencies to plan inventory. However, no single distribution is universally correct for all scenarios. Selecting the right one often involves a blend of theoretical reasoning and empirical testing. Goodness of fit tests compare observed data against the predictions of a chosen distribution, measuring discrepancies that might indicate a poor match. Graphical methods like QQ plots or histograms overlaid with theoretical curves also help evaluate appropriateness. Even when a distribution fits decently, real phenomena might deviate in subtle ways, prompting refinements or entirely new models. Continuous feedback between theory and observation drives progress. Interpreting probability distributions demands an appreciation for their limits as well as their powers. By assigning probabilities to all possible outcomes, these distributions quantify uncertainty, but they don't eliminate it. A model might say there is only a 1% chance of exceeding a certain threshold, yet improbable events still occur in the fullness of time. The 2008 financial crisis, for example, exposed the shortcomings of models that underestimated extreme risks. This doesn't undermine the utility of probability distributions. Rather, it emphasizes the need for cautious application and regular re-evaluation of assumptions. In essence, probability distributions provide structure to randomness, revealing hidden order behind seemingly unpredictable outcomes. They make it possible to estimate risks, plan for contingencies, and analyze the behaviors of complex systems with surprising accuracy. Whether you're rolling dice, scheduling servers to handle web traffic, or ensuring against unlikely catastrophes, these mathematical tools guide sensible decision-making. People often speak of chance as capricious or fickle, but probability distributions show that within large numbers, patterns emerge and persist. These patterns remain at the heart of statistical analysis, bridging the gap between uncertain data and concrete inferences. Every time you interpret a p-value, construct a confidence interval, or estimate error margins, a probability distribution underlies your calculations. Each new piece of data refines our grasp of the processes that shape our world, continually testing the fit of our chosen distribution. In doing so, we adapt to the intricacies of chance, gleaning insights that empower us to navigate uncertainty rather than be paralyzed by it. This dynamic interplay between theory and observation lies at the core of quantitative reasoning, reflecting an eternal dance between chaos and structure, variance and standard deviation. Picture a sprawling city skyline at dusk with buildings of various heights silhouetted against the setting sun. Some towers loom tall, their spires piercing the evening sky, while others nestle unobtrusively by busy streets. If you wanted a single number to describe this cityscape, an average height might come to mind, but it would fail to capture how the skyscrapers differ from smaller, low-rise structures. Variance and standard deviation serve as the statistical equivalents of observing those towering peaks and humble buildings alike, bringing attention to how widely or tightly values are distributed around the average. They reveal more than just a simple typical measure, offering a deeper dive into the underlying diversity within the data. At their core, both variance and standard deviation quantify spread, yet they do it in slightly different ways. Variance does so by taking the average of squared differences from the mean. Squaring those differences magnifies large deviations more than small ones, ensuring that extreme points in the data, like a particularly tall building, exert a greater influence on the measure. This approach creates a single numeric value that indicates, in aggregate, how much variation the dataset contains. A larger variance signals that points are scattered far from the mean, whereas a smaller variance suggests they bunch tightly together. Despite its utility, variance is often unintuitive when trying to relate it to real-world measurements because it comes in squared units. If the original data are in meters, for instance, variance ends up in meters squared. That's where standard deviation enters the scene. By taking the square root of the variance, the standard deviation returns the measure to the same scale as the data itself. Thus, if building heights are measured in meters, the standard deviation will also be in meters, making it easier to interpret. If the standard deviation is 10 meters, you immediately grasp that the typical building height deviates from the mean by about 10 meters. These two measures trace back to the same calculation pipeline. After identifying the mean, subtract it from each data point to find how far that point lies from the center. Those distances, both positive and negative, typically sum to zero if you just add them outright. To avoid cancellation, you square these differences, sum them up, and then divide by the appropriate number of observations. For a population variance, the denominator is simply the population size n. For a sample variance, statisticians usually apply what's called Bessel's correction, subtracting 1 from the sample size using n1 instead of n to produce an unbiased estimate. This detail might seem minor but can matter significantly in more formal analyses, ensuring that estimates reflect the broader population dynamics as accurately as possible. In practice, variance and standard deviation show up in virtually every area of quantitative work. Take the stock market, for instance. Analysts scrutinize the volatility of returns, and standard deviation becomes a shorthand for how bumpy a ride an investment might offer. If a stock's average return is 5%, but its standard deviation is 15%, that suggests swings in the stock price can be quite wide compared to its mean performance, warning potential investors of risk. Conversely, a safer investment might have a modest average return of 3% with a standard deviation of only 2%, implying returns tend to hover closer to that figure. Similarly, in academic settings, a teacher might be interested in understanding test scores. While the average score hints at how the class performs overall, the standard deviation reveals whether most students scored near that average, or if there's a large gap between high and low-scoring individuals. A small standard deviation points to a generally uniform understanding of the material, while a large one indicates a diverse range of performances, perhaps reflecting differences in study habits, backgrounds, or even the difficulty of certain questions. Sometimes, especially in manufacturing or quality control, engineers need to maintain tight tolerances around a target measurement. Imagine a factory producing bolts designed to fit into a machine part with minimal wiggle room. The diameter of the bolt might be set at 5 millimeters, but a quality inspector doesn't just care about the average diameter coming off the production line. They also want to ensure there is minimal variability, preventing frequent out-of-spec products. By monitoring the standard deviation, they can quickly spot if the process has started drifting, producing an increasing proportion of bolts that won't fit. Understanding variance and standard deviation also clarifies the concept of outliers, the data points that stand conspicuously apart from the rest. These outliers can inflate both measures dramatically because squaring large deviations accentuates them. In the city skyline analogy, imagine a megatower that dwarfs the next tallest building by hundreds of meters. Its presence pushes the variance and standard deviation upward, emphasizing how one extreme point impacts the overall distribution. Whether that outlier reflects a true anomaly, measurement error, or a valuable but rare occurrence is context-dependent. Analysts often investigate these points carefully, deciding whether to keep them, remove them, or apply transformations to reduce their influence. Another perspective is to see how variance or standard deviation interacts with the mean. Two data sets can share the same average, yet differ in their spread. Suppose two factories each produce bolts with an average diameter of exactly 5 millimeters, but Factory A's standard deviation is 0.2 millimeters, while Factory B's is 0.6 millimeters. Even though both factories have an equivalent mean, Factory B's final products will be much more inconsistent. Recognizing these differences prevents ill-informed conclusions drawn solely from the average. In advanced applications, variance can decompose the contributions of different factors in an analysis of variance, ANOVA. This approach partitions total variation in the data into categories of interest, such as treatment effects or random error, demonstrating how fundamental measures of spread inform statistical tests that compare means across multiple groups. Meanwhile, standard deviation enables normal distribution calculations to gauge how likely values are to fall within a certain range. For instance, in a normal distribution, about 68% of values lie within one standard deviation from the mean, and about 95% within two, forming the basis for many statistical inferences and confidence interval formulations. While the concept of squaring differences might appear arbitrary at first, there is deep mathematical justification for it. It simplifies calculus-based optimizations, ensures non-negative values, and aligns with fundamental properties like the Pythagorean theorem in multi-dimensional data spaces. However, alternative definitions of spread do exist. Absolute deviation from the mean avoids squaring values, though it's less tractable for many analyses. Others prefer robust measures like the interquartile range, which ignore extreme tails entirely. Yet, for all these other metrics, variance and standard deviation remain mainstays in both theory and practice, due to their compatibility with a wide array of statistical methods. Beyond these technicalities, an appreciation for variance and standard deviation can encourage better decision-making in everyday life. If two job offers come with the same salary average, but differ in the variability of potential bonuses, you might prefer the more consistent package or might gravitate toward the riskier option. If you track your daily step counts and see a high standard deviation from day to day, it could indicate inconsistent exercise habits, spurring you to aim for a steadier routine. Embracing spread as a vital piece of information avoids the trap of relying too heavily on a single metric, like an average. Even the world of sports analytics gains insight through measures of spread. A basketball team's scoring might average 110 points per game, but a large standard deviation implies their performance swings wildly. One night they score 140, the next only 80, suggesting unpredictability. The same principle applies to individual athletes, where coaches track consistency over a season. Higher variance suggests episodes of brilliance interspersed with off nights, while lower variance implies steadiness. Whether that's desirable depends on the context. Some teams crave the consistent performer, while others might gamble on peak potential. In essence, variance and standard deviation go hand in hand, tracing out the contours of how data scatter around a central point. Without these measures, analyses could be misleading, telling only half the story by focusing on averages. From finance to education, engineering to healthcare, the difference between a narrow distribution and a wide one can radically shift interpretations and plans. By integrating measures of central tendency with an understanding of spread, decision-makers gain a fuller view, making more nuanced and responsible choices. Just as the skyline's dramatic silhouette reveals the city's architectural diversity, variance and standard deviation reveal the richness and sometimes the unpredictability of data lurking just beyond the simple average. Confidence intervals. A fortune teller gazing into a crystal ball can't pinpoint the future with absolute clarity, but she can provide a range of possible outcomes. Confidence intervals serve a similar function in statistics, giving us a plausible range where an unknown parameter, often a population mean, might lie, based on what we observe in a sample. Rather than guaranteeing a single figure, these intervals embrace uncertainty. By specifying a confidence level, such as 95%, we declare how often repeated samples and intervals would capture the true value if we replicated our study many times under the same conditions. Despite their name, confidence intervals don't deliver absolute proof, but they do give a more nuanced, probabilistic framework for interpreting estimates. To see why confidence intervals matter, compare them with simple point estimates. Suppose you measure the average weight of apples in an orchard by randomly sampling 100 apples. You compute a mean of 150 grams, but that figure alone doesn't reveal how close you might be to the true orchard-wide average. After all, you didn't weigh every apple on those trees. You only weighed a sample. There's always sampling error. Some subtle differences between the apples you picked and the ones you didn't. A confidence interval accounts for that by extending above and below your sample mean to form a band of plausible values. Perhaps that range is from 145 to 155 grams at a 95% confidence level. Interpreting it incorrectly, however, can lead to all sorts of misconceptions. Saying there's a 95% chance the population mean falls in that specific interval for your single experiment is technically not correct. The right interpretation is that if you repeated the experiment many times, each time constructing a 95% confidence interval, about 95% of those intervals would contain the true mean. The width of a confidence interval depends on several factors, including sample size, variability in the data, and the confidence level you choose. Larger samples generally yield narrower intervals because they reduce the uncertainty inherent in your estimate. If you measure 1,000 apples instead of 100, the orchard's average weight estimate stabilizes, making the confidence interval tighter. Similarly, lower variability. For instance, if your apple orchard is very uniform in the size of its fruit, allows for more precision. The choice of confidence level, 90%, 95%, 99%, or something else, also affects the interval's breadth. A higher confidence level demands a wider net. Saying you're 99% sure the true mean lies in a certain range forces you to cover more ground to ensure you capture the parameter that often. In everyday use, people gravitate toward 95% confidence intervals. It's a convention in many scientific fields, arguably arbitrary, but it balances the need for reasonably strong evidence without excessively broad intervals. Suppose a political poll suggests that 52% of voters favor candidate A. A margin of error, say plus or minus 3%, might reflect the 95% confidence interval around this estimate, extending from 49% to 55%. If candidate B's support is estimated at 50%, plus or minus 3%, there's enough overlap that drawing a firm conclusion about who's actually ahead might be premature. As sample size grows, the margin of error usually shrinks, giving pollsters more precise intervals. Confidence intervals don't exist just for means. They can be constructed for proportions, differences between means, regression coefficients, correlation estimates, or odds ratios in logistic regression. The logic remains the same. You generate a best guess, but also quantify the uncertainty around that guess, presenting a range. These intervals become particularly useful when deciding if a difference is practically significant. Two treatments in a medical trial might show similar average improvements, but if their confidence interval ranges overlap substantially, concluding one is definitively better might be hasty. Conversely, if you see minimal or no overlap, that's a stronger signal that the treatments differ in the broader population. One area where confusion often arises is the connection between confidence intervals and p-values in hypothesis testing. The link is there, but they serve slightly different communication goals. A p-value focuses on how unlikely your data, or something more extreme, would be if a null hypothesis is true, whereas a confidence interval attempts to depict an entire set of plausible values for a parameter. If a 95% confidence interval around a difference between two group means excludes 0, you'll typically find that a corresponding two-sided hypothesis test yields a p-value under 0.05. However, many statisticians now favor reporting intervals instead of or in addition to p-values, as intervals clarify the potential magnitude and direction of effects, not just statistical significance. Another subtlety arises around the notion that the true parameter is fixed, albeit unknown, while the interval is what shifts across repeated sampling. When you construct a specific 95% confidence interval from your particular sample, that interval either does or does not contain the true parameter. There's no repeated flipping of reality. The 95% figure reflects a long-run frequency across hypothetical replications, not a single trial probability. This is sometimes referred to as a frequentist interpretation. Bayesian methods use posterior intervals to represent different concepts of probability, but that delves into a different statistical philosophy. For many practical applications, though, the frequentist concept of confidence intervals remains a staple. Real-world complexity often forces adjustments to the simple scenarios taught in introductory courses. For instance, data might violate assumptions of normality or independence, or might come from a small, unevenly distributed sample. In such cases, analysts may use more advanced techniques, bootstrapping for example, to build confidence intervals empirically. Bootstrapping resamples the collected data repeatedly, each time computing the statistic of interest, building a distribution of estimates that informs the interval. This method imposes minimal assumptions about the underlying population and can be particularly valuable when dealing with unconventional data shapes. There's also a temptation to interpret confidence intervals as definitive boundaries, outside which results cannot lie. But as sample information grows or conditions change, new intervals might shift the plausible range. Even a well-constructed 95% interval can fail to include the true parameter 5% of the time, by definition. External factors, like measurement errors, biases in data collection, or unaccounted for variables, can also systematically skew the interval. In medical studies, for example, if participants who respond poorly to treatment drop out, the final data might not fairly represent the entire population. The confidence interval might then underestimate the actual variance, misleading doctors about the treatment's reliability. Despite these caveats, confidence intervals remain a go-to tool for transparent scientific reporting. Presenting them encourages a mindset that acknowledges uncertainty, prompting experts and the public alike to weigh the data's precision. Imagine a meteorologist who says, "We expect 3 inches of rain tomorrow, give or take half an inch." That's essentially offering a confidence interval, clarifying the expectation while hinting at the margin for error. When intervals are routinely provided in news stories about poll results or scientific studies, consumers of information develop a clearer sense of how sure or unsure we truly are. Over time, such a norm can reduce misunderstandings that arise from reporting only single-value estimates, which can inadvertently appear more certain than they really are. Organizations reliant on data-driven decisions, like financial institutions, healthcare providers, or tech companies, also benefit when confidence intervals guide planning. An online retailer forecasting holiday sales might say, "We predict selling between 90,000 and 110,000 units." This range underscores the possibility of over- or undershooting inventory needs, allowing managers to prepare contingencies. If the retailer only clung to a single figure, say 100,000 units, it might either run out of stock if demand soars, or overstock if demand falls short. Confidence intervals encourage balanced, probabilistic thinking. The bottom line is that confidence intervals inject nuance into statistical estimates, simultaneously confronting the uncertainty inherent in sampling. While a single mean or proportion might be easier to digest, that crisp number can hide how fragile or stable the finding may be under repeated observation. By contrast, an interval visually and numerically communicates a buffer zone that accounts for the possibility of sampling variation, measurement noise, and incomplete knowledge. That means better calibration of expectations. We can proceed with caution when intervals are wide, and proceed with more confidence when intervals narrow. The world rarely offers absolute certainty, but well-constructed confidence intervals shine a spotlight on the plausible range, bridging the gap between guesswork and informed decision-making. Correlation versus causation. Step into a bustling cafe, watch the myriad of people streaming in and out, and observe all the possible connections. Maybe those who sit together chat more, or perhaps people who prefer a certain table order, a specific drink. One might notice patterns, like a strong association between patrons who wear headphones and patrons who sit by the window. But does wearing headphones cause people to choose those window seats, or is some other factor at play, like wanting to escape noise? This situation highlights a classic dilemma in statistics and everyday thinking: the difference between correlation and causation. Correlation serves as a measure of how two variables move in relation to each other. When one variable increases, does the other also increase? Or does it tend to decrease? Or perhaps they move independently, with no consistent pattern. A correlation coefficient, often denoted by R, gives a numeric snapshot of this relationship, ranging from -1 to +1. A value near +1 indicates a strong positive correlation. As one value rises, so does the other. A value near -1 indicates a robust negative correlation. As one gets larger, the other declines. A correlation close to 0 means no obvious linear linkage. In the cafe, if you tallied data and found that people wearing headphones do indeed sit near windows 80% of the time, you might suspect a positive correlation. Yet even a perfect correlation doesn't guarantee cause and effect. Several traps emerge when we assume that just because two variables move in tandem, one must necessarily drive the other. One of the most basic scenarios is the possibility of a third variable, sometimes called a lurking variable. If you notice that ice cream sales correlate strongly with the number of drownings at the local beach, you might be tempted to theorize that eating ice cream leads to riskier swimming. The hidden factor, however, might just be temperature. On hot days, both ice cream consumption and beach attendance go up, and with more swimmers in the water, the unfortunate chance of drownings naturally increases. The correlation between ice cream sales and drownings is real, but it emerges from a shared cause, heat and summertime behavior, rather than one causing the other. Another scenario is reverse causation, which flips our presumed cause and effect. Suppose you find that people who are stressed out sleep less. At first glance, you might assume that stress causes insomnia, but it could also be that a lack of sleep fosters stress, or that the relationship flows in both directions. Without proper controls or experimental design, one can't unravel which variable triggers the other. In fields like economics, health, or education, untangling these directions can be notoriously difficult. Correlation alone doesn't provide enough insight to declare a one-way link. That said, correlations are invaluable for highlighting patterns worthy of deeper study. A strong correlation can flag an avenue for further investigation, prompting carefully designed experiments or additional data collection. In epidemiology, for instance, a correlation between smoking and lung cancer initially signaled a potential cause and effect relationship. Over time, repeated studies accumulated evidence, controlling for confounders and investigating biological mechanisms. That process built the case that smoking indeed causes a higher risk of lung cancer. Observing the correlation alone wasn't sufficient to draw that conclusion. The rigorous testing confirmed it. Establishing causation often requires controlled experiments. Think of randomized controlled trials, RCTs, in medicine. If researchers want to test a new drug, they randomly assign participants to either receive that drug or a placebo. Randomization helps balance out lurking variables such as age or underlying health conditions across the groups. By measuring outcomes over time, they can be more confident that any difference observed stems from the drug rather than from confounding factors. Correlation may be evident in such a scenario, but the randomization and experimental control are what strengthen a causal claim. In many domains, though, randomized experiments aren't feasible. You can't randomly assign people to smoke or not smoke for an ethics-compliant study, and you can't randomly decree that people must live in a certain neighborhood. Observational studies, though valuable, rely on statisticians to apply sophisticated methods, like propensity score matching or instrumental variables, to approximate experimental conditions. Even with these advanced techniques, strong caution remains. Perfectly disentangling correlation from causation still proves tricky, and conclusions often come packaged with caveats or ranges of uncertainty. Media headlines, however, frequently gloss over the nuance. It's no surprise that study finds eating chocolate correlates with brain health can morph in the public mind into chocolate causes a healthy brain. People latch on to the simpler story. Readers should examine the study's design and the researcher's own statements before concluding that one variable truly causes the other. Even well-intentioned reporters can inadvertently spin correlation as an ironclad causal relationship, especially when the data tell a compelling but incomplete narrative. Beyond lurking variables and reverse causation, there's also the possibility of spurious or coincidental correlations. With large datasets and modern computing power, analysts can mine for associations among thousands or millions of variables. Inevitably, some pairs of variables will appear strongly correlated simply by chance. Online, humorous examples abound of how the number of Nicolas Cage film appearances in a year correlates with swimming pool drownings. When data are plentiful, random coincidences will crop up. That's why replication and theoretical grounding are crucial. If an observed relationship lacks a logical explanation or evidence across multiple studies, it may be nothing more than a statistical artifact. Sometimes correlation is enough for practical decisions, even if causation is murky. In predictive modeling, a strong correlation between an input variable and an outcome can improve forecasts. For instance, if online purchases correlate strongly with the number of clicks on a product page, a marketer might exploit that correlation to target users who visit those pages frequently. They might not need to demonstrate that clicking causes purchases, only that it's a strong indicator of someone likely to buy. Still, it's always better to understand the underlying dynamics to avoid reliance on fragile or misleading associations, especially if the environment changes or the correlation breaks down under new conditions. From a scientific standpoint, the ultimate goal is not just to see if two variables dance together in the data, but why they dance and who leads. Conducting robust studies, articulating hypotheses, and systematically eliminating alternative explanations all pave the road toward causation. Observational data demand caution. Even when advanced statistical methods show strong associations, subtle biases or unmeasured confounders can remain. Meta-analyses that combine multiple studies can strengthen our confidence, but they can't inject experimental rigor where none existed. Understanding this distinction between correlation and causation fosters more critical thinking. When you see news articles linking certain behaviors to certain outcomes, ask yourself how the data were collected. Was it an experiment, an observational study, or just anecdotal reports? Were the groups randomly assigned, or might people have self-selected into behaviors that correlate with other hidden factors? Asking these questions separates those who interpret statistics responsibly from those who fall prey to the nearest sensational headline. Education about correlation and causation can begin in the simplest, everyday observations. Why does traffic seem worse when it rains? Does the rain cause traffic congestion? Likely yes, but maybe there's more to it, like reduced visibility, slower driving speeds, and people opting for cars over public transportation. The question then becomes how to isolate the direct effect of rain from these other factors. By habitually thinking through potential lurking variables and alternate explanations, one grows adept at recognizing the complexities that underlie even simple causal claims. As a final note, it's important to remember that correlation is not the enemy. On the contrary, it's a critical clue. Identifying correlations is often the first step toward deeper analysis. It flags relationships that might merit exploration and can guide subsequent research, experiments, and policy. A correlation might be spurious, might reflect reverse causation, or might indeed hint at causality. The key is distinguishing which is which, and that can't be done by correlation alone. It requires a mix of study design, repeated evidence, theoretical plausibility, and sometimes sheer scientific sleuthing. If you keep these subtleties in mind, you'll be better equipped to navigate that bustling cafe of data we all inhabit without mistaking a passing association for a guaranteed cause and effect relationship. Outliers and anomalies. Suppose you're analyzing a set of monthly sales figures for a small online retailer. For nearly every month, revenue hovers in a certain range, reflecting steady customer traffic. Then you spot one month where sales shoot through the roof, dwarfing the other data points. That single extraordinary figure stands out like a neon sign in a darkened room. In statistics, these extreme or highly unusual observations are known as outliers or anomalies, and they can alter your entire perspective on a data set. The line between an informative outlier and a misleading piece of noise can be murky, forcing analysts to tread carefully before deciding how to handle such peculiar data. Outliers can come from genuine phenomena, such as a marketing campaign that went unexpectedly viral, or an extremely large order from a single client. They can also stem from data entry slip-ups, sensor malfunctions, or sampling peculiarities. When measurements deviate dramatically from the rest, it's rarely wise to ignore them outright. They might contain crucial details. That said, blindly including them in every statistical calculation can skew results or overshadow more typical patterns. The crux of the challenge lies in identifying which anomalies represent genuine signals worth examining, and which ones are simply errors that pollute the overall picture. Identifying outliers starts with looking at how data distribute themselves. In a normal distribution, values cluster around the mean, forming a bell shape. Outliers appear far out in the tails, well beyond most observations. Analysts sometimes apply simple rules like marking any point beyond 3 standard deviations from the mean as a potential outlier. Another approach uses interquartile ranges, flagging points that lie more than 1.5 or 3 times the interquartile range, above the third quartile or below the first quartile. However, these numeric guidelines are not infallible. They may misclassify unusual but valid data as anomalies, or miss genuinely improbable values that happen to cluster close to other points. Context frequently trumps raw formulas. A single scorching hot day in a weather dataset might not qualify as an error if seasonal heat waves are common. On the other hand, a negative price in a sales log is almost certainly a mistake. Domain knowledge helps determine which points are plausible. If you're dealing with biological measurements, you might already know that certain variables cannot go below 0, so any negative reading signals a problem in data collection. In engineering contexts, sensors might report impossible voltages due to interference. Without an awareness of the physical or business constraints, purely statistical rules can mislead. Even once you've identified unusual data, deciding how to handle them demands judgment. In some projects, those extreme observations might be the primary interest. Fraud analysts watch for anomalies in credit card transactions because these surprising patterns can reveal unauthorized activity. Similarly, cybersecurity experts search for unusual network traffic that may indicate a breach. Here, outliers are precisely what analysts want to detect and investigate further. In other scenarios, though, outliers might obscure more common trends. For instance, if a single monthly sales figure is vastly higher due to an unrepeatable one-off event, it may distort calculations of average revenue, making forecasts unrealistic for future months. Some researchers use robust statistical methods that mitigate the impact of outliers without necessarily discarding them. Unlike the arithmetic mean, which can be dragged off course by a small number of extreme values, measures like the median or trimmed means are less susceptible to large deviations. Trimming, for instance, involves removing a specified percentage of the smallest and largest data points before calculating the mean. Windsorizing reshapes extreme values to the boundary of a percentile range. These techniques reduce the undue influence of outliers on summary statistics, though they also alter the dataset and must be used with care. In large datasets, outliers can cluster or emerge in groups, creating what's termed multivariate outliers. Rather than being abnormal in just one dimension, these points deviate across several variables simultaneously. Imagine you're evaluating shipping times, package weights, and customer locations. A single package that took much longer than average might appear suspicious, but if that package was also unusually heavy and headed to a remote destination, the delay could be justifiable. Multivariate outlier detection techniques check for unusual combinations of variables, which demands more complex methods like Mahalanobis distance or isolation force in machine learning contexts. Anomalies can take other forms too. A time series may exhibit spikes or sudden shifts, behavior that a simple summary might overlook. Monitoring website traffic often reveals consistent hourly or daily patterns, but an unexpected surge in requests late at night could indicate a viral mention on social media or a distributed denial of service attack. Tools that focus on time series anomaly detection might compare incoming data with seasonally adjusted expectations, highlighting points that deviate drastically from projected behavior. If the departure is legitimate, the spike might signal a unique opportunity to investigate what caused the surge in interest. If it's malicious or erroneous, the outlier is a red flag prompting rapid intervention. Even within machine learning and predictive modeling, outliers present a dilemma. Models such as linear regression or neural networks can overfit to extreme values, distorting their performance. Some algorithms are more robust by design. For instance, tree-based methods may handle outliers more gracefully, splitting the data according to decision boundaries, rather than calculating an average response. When data scientists suspect anomalies could harm model accuracy, they might choose to label certain points as outliers beforehand, or incorporate anomaly detection steps in the pipeline. Yet these decisions can reduce the training set, possibly omitting valid data that actually hold important insights. An especially tricky aspect is determining whether outliers represent a separate subgroup. Picture a dataset of consumer spending patterns. Most customers have moderate expenditures, but a small group spends far more than the average, perhaps because they operate businesses or earn significantly higher incomes. If you treat those high-spending individuals as anomalies and remove them, you might lose an entire segment of the market that merits dedicated strategies. Recognizing subpopulations is often more productive than dismissing them outright. Clustering methods can reveal whether extreme points form a coherent cluster or simply sit alone in the data space. And the handling of outliers can also differ across industries. Pharmaceutical researchers scrutinize abnormal lab results to ensure they aren't missing a dangerous side effect. Financial auditors see anomalies in accounting ledgers as warning bells for potential fraud or misstatements. Social scientists might suspect that respondents who complete a lengthy survey in a fraction of the expected time are inattentive or gaming the system. Each use case demands tailored rules shaped by domain expertise and the consequences of missing or misclassifying anomalies. Ethical questions can arise if researchers mistakenly label real individuals as anomalies. For example, an online platform might flag a legitimate user's behavior as suspicious, leading to an account suspension. Even in healthcare, an unusual lab reading could prompt unnecessary concern or medical procedures if taken out of context. The challenge is to strike a balance between not overlooking crucial information and not overreacting to every statistical quirk. Excluding outliers purely to achieve neat results can mask valuable information or produce misleading conclusions, while overemphasizing them can blow inconsequential oddities out of proportion. Ultimately, the presence of outliers highlights the inherent complexity of real-world data. While neat statistical assumptions often revolve around tidy distributions without extreme values, reality rarely behaves so predictably. Sometimes an outlier is simply the product of randomness in a large data set. Other times, it's the harbinger of a breakthrough discovery. Perhaps the retailer's sudden sales spike came from a new influencer mention or a viral ad campaign, a vital clue that could shape future marketing strategies. Treating anomalies with skepticism, but remaining open to the story they might tell, is often the key to unlocking novel insights. No universal recipe prescribes when to keep or remove outliers. Analysts must weigh each situation's context, the reliability of measurement, and the impact on outcomes. Techniques like robust statistics, data transformations, or specialized anomaly detection algorithms can help navigate the murky territory between ignoring outliers and letting them hijack the entire analysis. In the end, these weird data points remind us that genuine patterns sometimes hide in the extremes. A well-chosen approach that acknowledges their potential significance and investigates their origins can turn what first appears as messy data into a catalyst for deeper understanding, better decisions, and unexpected innovation. Bayesian Statistics. In the quiet hours of a bustling newsroom, journalists rely on more than just instinct to break the latest stories. They depend on data to shape their narratives. As new information pours in, their understanding of the unfolding events evolves, allowing them to update their reports with greater accuracy and insight. This dynamic interplay between accumulating evidence and shifting perspectives mirrors the essence of Bayesian statistics, a powerful framework that transforms how we interpret data by continuously updating our beliefs in light of new information. Bayesian statistics is fundamentally about learning and adaptation. Unlike traditional frequentist approaches, which often view parameters as fixed and data as random, Bayesian methods treat both parameters and data as part of a probabilistic system. At its core lies Bayes' theorem, a mathematical formula that provides a way to update the probability of a hypothesis based on new evidence. This theorem bridges our prior beliefs with the likelihood of observed data, resulting in a posterior belief that reflects both sources of information. To grasp the significance of Bayesian statistics, consider the classic example of diagnosing a disease. Suppose a patient undergoes a medical test that has a known accuracy rate. Initially based on the prevalence of the disease in the general population, a doctor holds a prior belief about the likelihood that the patient has the disease. When the test result comes back positive, Bayes' theorem helps the doctor update this belief by combining the prior probability with the test's likelihood, yielding a more accurate posterior probability of the disease. This updated probability accounts for both the initial belief and the new evidence provided by the test result. This iterative updating process is what makes Bayesian statistics so versatile and intuitive. In real-world scenarios, information is rarely static. Whether tracking the spread of a virus, predicting stock market trends, or refining machine learning models, the ability to adjust probabilities as new data emerges is invaluable. Bayesian methods offer a coherent and flexible approach to incorporate ongoing information, ensuring that our beliefs remain aligned with the latest evidence. A key component of Bayesian analysis is the prior distribution, which encapsulates our initial beliefs about a parameter before observing any data. The choice of prior can range from non-informative, representing complete uncertainty, to highly informative, reflecting strong existing knowledge. For instance, in environmental studies, researchers might use historical climate data to inform their priors when predicting future temperature changes. As new measurements are taken, the prior is updated with the likelihood of the observed data, leading to a posterior distribution that blends past knowledge with present observations. The posterior distribution is the cornerstone of Bayesian inference. It provides a full probabilistic description of the parameter after considering the new data. Unlike point estimates, which offer a single value, the posterior distribution captures the entire range of plausible values, along with their associated probabilities. This richness allows for more nuanced decision-making, as it quantifies the uncertainty and variability inherent in the estimates. For example, a business analyst forecasting quarterly sales can use the posterior distribution to assess not just the expected sales figure, but also the confidence in that expectation, enabling more informed strategic planning. Bayesian statistics also shines in its ability to handle complex models and hierarchical structures. In hierarchical Bayesian models, parameters themselves can have their own priors, creating layers of probability distributions that mirror real-world complexities. This is particularly useful in fields like psychology or ecology, where data may be nested or grouped in meaningful ways. By modeling these dependencies explicitly, Bayesian methods provide more accurate and interpretable results, accommodating the intricacies of diverse datasets. One of the most compelling advantages of Bayesian statistics is its interpretability. The probabilistic statements derived from Bayesian analysis align closely with human intuition. Phrases like, "There is a 95% probability that the parameter lies within this interval," resonate more naturally than the frequentist counterparts, which rely on long-run frequencies and repeated sampling interpretations. This clarity makes Bayesian methods particularly appealing in communication-heavy fields, such as public health or policymaking, where conveying uncertainty and confidence clearly is crucial. Computational advancements have significantly expanded the applicability of Bayesian methods. Techniques like Markov Chain Monte Carlo, MCMC, allow statisticians to approximate posterior distributions for complex models that are analytically intractable. These algorithms simulate numerous samples from the posterior, enabling the estimation of probabilities and the exploration of parameter spaces that would otherwise be inaccessible. Software tools such as Stan, Bugs, and PyMC have democratized Bayesian analysis, making it accessible to a broader audience and facilitating its integration into various research workflows. Despite its strengths, Bayesian statistics does face challenges and criticisms. The choice of prior can be subjective, potentially introducing bias if not carefully considered. Critics argue that the reliance on prior information can make Bayesian results less objective compared to frequentist methods. However, proponents counter that all statistical methods incorporate some form of prior belief, whether explicit or implicit, and that Bayesian methods offer a transparent and systematic way to incorporate and assess these beliefs. Sensitivity analyses, where different priors are tested, can help mitigate concerns about subjectivity and demonstrate the robustness of the conclusions. Another hurdle is the computational intensity of Bayesian methods, especially for large datasets or highly complex models. While advancements in algorithms and computing power have alleviated some of these issues, Bayesian analysis can still be resource-demanding compared to simpler frequentist techniques. Nevertheless, the benefits of a more comprehensive probabilistic framework often outweigh the computational costs, particularly as hardware continues to improve and more efficient algorithms are developed. Bayesian statistics also fosters a deeper connection between theory and practice. By formalizing the process of updating beliefs, it encourages a continuous learning mindset, where models evolve as new data becomes available. This adaptability is crucial in fast-paced environments, such as financial markets or real-time monitoring systems, where static models can quickly become outdated. Bayesian approaches naturally incorporate this dynamism, ensuring that analyses remain relevant and accurate over time. Educational efforts have also played a role in the growing popularity of Bayesian statistics. As more courses and resources emphasize Bayesian thinking, new generations of statisticians and data scientists are embracing its principles and methodologies. This shift is evident in the increasing prevalence of Bayesian techniques in academic research, industry applications, and even everyday decision-making tools. The intuitive appeal and practical benefits of Bayesian methods make them a valuable addition to any analytical toolkit. In the realm of machine learning, Bayesian methods offer a principled approach to uncertainty quantification and model averaging. Bayesian neural networks, for instance, integrate prior distributions over weights and biases, allowing for the assessment of uncertainty in predictions. This capability is essential for applications where confidence in predictions matters, such as autonomous driving or medical diagnosis. By leveraging Bayesian principles, machine learning models can provide not just predictions, but also confidence levels, enhancing their reliability and trustworthiness. Moreover, Bayesian statistics facilitates the integration of diverse data sources and types. In multimodal data sets, where different types of data are combined, such as textual, numerical, and image data, Bayesian frameworks can coherently incorporate information from each source. This integration enhances the robustness and accuracy of models, enabling more comprehensive analyses that reflect the multifaceted nature of real-world phenomena. Whether synthesizing data from various sensors in an IoT system or combining survey responses with behavioral data, Bayesian methods offer a unified approach to handling complexity. The philosophy underpinning Bayesian statistics extends beyond mere calculations. It embodies a way of thinking about uncertainty and learning. It encourages a mindset where beliefs are not static, but evolve with experience and evidence. This perspective aligns closely with scientific inquiry, where hypotheses are continually tested and refined based on new discoveries. By embracing uncertainty and systematically updating beliefs, Bayesian statistics fosters a more flexible and realistic approach to understanding the world. In summary, Bayesian statistics revolutionizes how we interpret data by providing a structured method for updating our beliefs in the face of new evidence. Its foundation on Bayes' theorem enables a seamless blend of prior knowledge and observed data, resulting in comprehensive and interpretable posterior distributions. The adaptability, interpretability, and robust theoretical underpinnings of Bayesian methods make them indispensable in a wide array of fields, from medicine and finance to machine learning and public policy. As data continues to grow in volume and complexity, Bayesian statistics stands out as a versatile and powerful tool, guiding us through the uncertainties and helping us make informed, evidence-based decisions. Embracing Bayesian thinking not only enhances our analytical capabilities, but also aligns our statistical practices with the continuous evolving nature of knowledge itself. ANOVA, analysis of variance. Picture a grand orchestra tuning up before a performance. Each section, strings, woodwinds, brass, and percussion, plays its own notes, harmonizing to create a unified symphony. But what if one section is slightly out of tune? Detecting these subtle differences ensures that the entire orchestra performs flawlessly. In the realm of statistics, ANOVA, or analysis of variance, serves a similar purpose. It allows researchers to determine whether there are statistically significant differences between the means of three or more independent groups, ensuring that variations within the data are understood and accounted for. Much like an orchestra, maintains harmony among its diverse instruments. At its core, ANOVA is a statistical technique used to compare the means of multiple groups to ascertain if at least one group mean is different from the others. Unlike simple t-tests, which are limited to comparing two groups, ANOVA scales elegantly to handle three or more groups simultaneously. This capability is invaluable in numerous fields, from agriculture testing different fertilizer types to medical studies comparing the efficacy of multiple treatments. By analyzing the variance within and between groups, ANOVA helps identify whether observed differences are likely due to true effects or merely random fluctuations. The foundation of ANOVA lies in partitioning the total variability observed in the data into components attributable to different sources. Imagine measuring the heights of plants subjected to various fertilizers. The total variance in plant heights includes both the variance within each fertilizer group, how much individual plant heights vary under the same fertilizer, and the variance between the groups, differences in average heights due to different fertilizers. ANOVA quantifies these variances to determine whether the fertilizer type has a significant impact on plant growth. There are several types of ANOVA, each suited to different experimental designs. The most common is one-way ANOVA, which assesses the effect of a single factor with multiple levels. For instance, if a psychologist wants to compare the stress levels of individuals exposed to different types of meditation techniques, one-way ANOVA would be appropriate. Here, the single factor is the type of meditation, and each technique represents a level within that factor. Two-way ANOVA extends this concept by evaluating the influence of two independent factors simultaneously and examining any interaction effects between them. For example, suppose an educator wants to study the impact of teaching method, traditional versus interactive, and study environment, quiet versus noisy, on student performance. Two-way ANOVA can assess not only the main effects of teaching method and study environment, but also whether the effectiveness of a teaching method depends on the study environment. Beyond one-way and two-way ANOVA, there are more complex forms like repeated measures ANOVA, which accounts for measurements taken from the same subjects under different conditions or over time. This is particularly useful in longitudinal studies where researchers track changes within the same individuals, such as monitoring blood pressure before, during, and after a dietary intervention. The mathematical underpinnings of ANOVA involve comparing variances to determine significance. The core concept revolves around the F statistic, a ratio of the variance between groups to the variance within groups. A higher F value suggests that the group means are more spread out than would be expected by chance alone, indicating a significant effect. To calculate the F statistic, ANOVA divides the total sum of squares, a measure of total variability, into the sum of squares between groups and the sum of squares within groups. These are then normalized by their respective degrees of freedom to compute mean squares, which form the basis for the F ratio. Interpreting ANOVA results requires understanding the p-value associated with the F statistic. A low p-value, typically less than 0.05, indicates that the observed differences between group means are unlikely to have occurred by random chance, leading to the rejection of the null hypothesis, which states that all group means are equal. However, ANOVA itself does not specify which specific groups differ from each other. To pinpoint these differences, post hoc tests like Tukey's HSD, honestly significant difference, or Bonferroni corrections are employed, ensuring that multiple comparisons do not inflate the type I error rate. One of the primary assumptions of ANOVA is homogeneity of variances, meaning that the variance within each group should be roughly equal. Violations of this assumption can lead to inaccurate conclusions. To check for homogeneity, tests such as Levine's test or Bartlett's test are commonly used. If the assumption is violated, alternative methods like Welch's ANOVA, which does not assume equal variances, or non-parametric alternatives like the Kruskal-Wallis test, may be more appropriate. Another key assumption is the normality of residuals, which assumes that the differences between observed and predicted values follow a normal distribution. While ANOVA is relatively robust to deviations from normality, especially with larger sample sizes, significant departures can affect the validity of the results. Visual inspections using QQ plots or statistical tests like the Shapiro-Wilk test can help assess normality. Transformations of the data or bootstrapping techniques might be necessary if normality is severely violated. ANOVA's versatility extends to its application in various disciplines. In agriculture, it helps determine the most effective crop treatments by comparing yields across different fertilizer types. In marketing, Businesses might use ANOVA to evaluate consumer preferences across multiple product variations. In psychology, researchers assess the impact of different therapeutic interventions on mental health outcomes. The method's ability to handle multiple comparisons efficiently makes it a cornerstone in experimental design and analysis. Despite its strengths, ANOVA is not without limitations. It primarily detects whether any differences exist, but does not provide the magnitude of these differences. Effect size measures, such as ETA squared or omega squared, complement ANOVA by quantifying the proportion of total variance attributed to the factors being studied. These measures offer a more comprehensive understanding of the practical significance of the findings, beyond mere statistical significance. Moreover, ANOVA is sensitive to outliers, which can disproportionately influence the variance estimates. Anomalous data points can inflate the within-group variance, masking true differences between group means or falsely suggesting significant effects. Therefore, identifying and addressing outliers through robust statistical techniques or data transformation is crucial to ensure the integrity of the ANOVA results. In the era of big data, ANOVA continues to evolve, integrating with more advanced statistical and machine learning techniques. Multivariate ANOVA, MANOVA, for instance, extends the framework to handle multiple dependent variables simultaneously, allowing for the assessment of how factors influence several outcomes at once. This is particularly useful in fields like genetics or social sciences, where complex interdependencies are the norm. Additionally, the rise of Bayesian ANOVA introduces a probabilistic perspective, incorporating prior knowledge and updating beliefs based on observed data. This approach offers a more flexible and nuanced interpretation of results, accommodating uncertainty and partial information in ways that traditional frequentist ANOVA does not. Bayesian methods can be particularly advantageous in exploratory research, or when dealing with limited sample sizes, where incorporating prior information can enhance the robustness of conclusions. Educational initiatives have also embraced ANOVA's importance, integrating it into curricula across disciplines to equip students with essential analytical skills. Understanding ANOVA not only enhances statistical literacy, but also fosters critical thinking, enabling students to design robust experiments and interpret complex data effectively. As data-driven decision-making becomes increasingly integral to various industries, proficiency in ANOVA remains a valuable asset for aspiring professionals. In practical settings, ANOVA aids in optimizing processes and improving quality control. Manufacturers might use ANOVA to compare defect rates across different production lines, or to evaluate the impact of various input materials on product quality. By systematically analyzing these differences, organizations can identify best practices, streamline operations, and enhance overall efficiency. Similarly, in healthcare, ANOVA helps compare patient outcomes across different treatment protocols, guiding evidence-based practices and policymaking. Moreover, ANOVA's integration with software tools has democratized its accessibility, allowing practitioners to perform complex analyses with relative ease. Statistical software like R, Python's SciPy library, SPSS, and SAS provide built-in functions for conducting ANOVA, handling calculations, and visualizing results. These tools also offer extensive documentation and community support, making ANOVA accessible to both novices and experienced statisticians alike. To further illustrate, consider a scenario in educational research. Suppose a university wants to evaluate the effectiveness of 3 different teaching methods on student performance. By administering tests across groups exposed to each method, ANOVA can determine whether the teaching methods yield significantly different average scores. If ANOVA indicates a significant difference, Post hoc tests can identify which specific methods differ, guiding educators in adopting the most effective strategies. This systematic approach ensures that decisions are grounded in empirical evidence rather than anecdotal impressions. In environmental science, ANOVA helps assess the impact of various conservation strategies on biodiversity. By comparing species counts across different protected areas managed with distinct approaches, researchers can identify which strategies are most effective in preserving ecosystems. This evidence-based insight is crucial for developing policies that balance human activities with environmental sustainability. Despite its widespread use, mastering ANOVA requires a solid understanding of its principles and assumptions. Researchers must design experiments thoughtfully, ensuring that groups are comparable and that data collection methods are consistent. Properly interpreting ANOVA results also demands attention to context, effect sizes, and potential confounders. By adhering to best practices and leveraging complementary statistical techniques, analysts can harness ANOVA's full potential to uncover meaningful insights from their data. ANOVA is a powerful and versatile tool in the statistical arsenal, enabling the comparison of multiple groups with efficiency and precision. Its ability to partition variance and identify significant differences across groups makes it indispensable in research, industry, and beyond. By understanding its foundations, applications, and limitations, practitioners can apply ANOVA effectively to drive informed decisions and foster advancements across diverse domains. Just as an orchestra relies on harmony among its sections, ANOVA ensures that the intricate interplay of multiple groups is analyzed harmoniously, revealing the symphony of insights hidden within the data. Chi-square tests. Imagine you're a detective in a bustling city, trying to uncover hidden connections between seemingly unrelated events. You notice that every time a new cafe opens downtown, the number of foot traffic accidents in the area spikes. Intrigued, you wonder if there's a real link between the cafe's presence and the accidents, or if it's just a coincidence. This is where chi-square tests come into play, acting as your statistical magnifying glass to reveal whether such patterns are genuine or merely random flukes. Chi-square tests are essential tools in statistics used to explore relationships between categorical variables. Unlike numerical data, which deals with quantities and measurements, categorical data involves classifications or groupings such as types of products, survey responses, or demographic categories. For instance, you might want to know if there's a connection between a person's favorite type of music, rock, pop, jazz, and their preferred mode of transportation, car, bike, public transit. The chi-square test helps determine whether the observed distribution of preferences across categories is significantly different from what we'd expect if there were no association at all. At the heart of the chi-square test is the comparison between what we observe in our data and what we would expect to see if there were no relationship between the variables. Continuing with our detective analogy, if the cafe opening was truly influencing the accident rates, we would see a consistent pattern where accidents increase specifically in areas with new cafes, beyond what random chance would predict. The chi-square test quantifies this by analyzing the frequencies of occurrences in each category and assessing whether deviations from expected frequencies are large enough to suggest a real association. One common application of chi-square tests is in market research. Imagine a company launching a new product and wanting to understand if its appeal varies across different age groups. By collecting data on product preferences among various age brackets, the chi-square test can reveal whether certain age groups are more inclined to favor the product, or if the preferences are uniformly distributed. This insight allows the company to tailor its marketing strategies more effectively, targeting demographics that show a stronger preference and potentially increasing sales. In the realm of healthcare, chi-square tests play a crucial role in identifying associations between risk factors and health outcomes. For example, Researchers might investigate whether there's a relationship between smoking status, smoker, non-smoker, and the incidence of lung disease, yes, no. By comparing the observed numbers of smokers and non-smokers with and without lung disease to what would be expected if smoking had no effect, the test can help determine if smoking is significantly associated with higher rates of lung disease. Such findings can inform public health policies and anti-smoking campaigns, ultimately contributing to better health outcomes. Educational institutions also benefit from chi-square tests when examining the relationship between student characteristics and academic performance. Suppose a school wants to explore whether there's an association between students' participation in extracurricular activities, yes, no, and their academic achievements, high, medium, low. By analyzing the distribution of academic performance across activity participation, the chi-square test can indicate whether involvement in extracurriculars is linked to better academic results, or if the observed differences are simply due to chance. Beyond these examples, chi-square tests are widely used in social sciences to study patterns in survey data. For instance, sociologists might investigate whether there's a relationship between gender and voting preference in an election. By categorizing respondents based on gender and their chosen candidate, the chi-square test can reveal if voting patterns differ significantly between males and females, providing valuable insights for political campaigns and understanding voter behavior. One of the strengths of chi-square tests is their simplicity and versatility. They can be applied to a wide range of scenarios involving categorical data, making them invaluable across various fields such as business, healthcare, education, and social sciences. However, to ensure accurate results, certain conditions must be met. The data should consist of independent observations, meaning that the occurrence of one event doesn't influence the occurrence of another. Additionally, the sample size should be sufficiently large to provide reliable results, as very small samples might not capture the true underlying patterns. When conducting a chi-square test, the first step is to create a contingency table, which organizes the data into rows and columns based on the categories of the two variables being studied. This table displays the frequency of observations in each category combination, providing a clear visual representation of the data. For example, in the study of music preferences and transportation modes, the rows might represent different music genres, while the columns represent various transportation methods. The table would then show how many individuals prefer each combination, such as how many rock music fans prefer cars versus bikes. Once the contingency table is established, the chi-square test evaluates whether the differences between the observed frequencies and the expected frequencies, if there were no association, are significant. This evaluation involves calculating a test statistic that measures the overall discrepancy between observed and expected counts. If the test statistic indicates that the observed patterns are unlikely to have occurred by chance alone, the test suggests that there is a meaningful association between the variables. Interpreting the results of a chi-square test involves comparing the test statistic to a critical value from the chi-square distribution, which depends on the desired level of confidence and the degrees of freedom related to the number of categories. A significant result means that the null hypothesis, no association, can be rejected, indicating that there is likely a relationship between the variables. On the other hand, a non-significant result suggests that any observed differences are consistent with random variation, and no strong association exists. While chi-square tests are powerful, they also have limitations. They can only detect associations, not causation. Even if a significant association is found, it doesn't imply that one variable causes the other to change. For instance, finding a link between cafe openings and traffic accidents doesn't mean that the cafes are causing the accidents. There might be other factors at play, such as increased foot traffic in general, Additionally, chi-square tests require categorical data, so they aren't suitable for analyzing relationships between continuous variables without first categorizing them. Another consideration is the potential for multiple comparisons to inflate the likelihood of finding significant associations by chance. When conducting multiple chi-square tests within the same dataset, the probability of encountering at least one false positive increases. To mitigate this, researchers often adjust their significance thresholds or use techniques like the Bonferroni correction to maintain the overall confidence level. Despite these challenges, chi-square tests remain a cornerstone of statistical analysis for categorical data. They provide a straightforward method for uncovering relationships and patterns that might otherwise go unnoticed, guiding informed decision-making and deeper investigations. By systematically comparing observed and expected frequencies, chi-square tests help translate raw data into meaningful insights, much like a detective piece together clues to solve a mystery. In practice, the process of conducting a chi-square test is facilitated by various statistical software and tools. Programs like R, Python's SciPy library, SPSS, and Excel offer built-in functions to perform these tests, handle contingency tables, and visualize the data. These tools streamline the analysis, allowing researchers to focus on interpreting the results rather than getting bogged down in manual calculations. To ensure the validity of a chi-square test, it's crucial to carefully design the study and collect data that meet the test's assumptions. Random sampling, adequate sample size, and clear category definitions are essential for reliable results. Additionally, understanding the context and underlying mechanisms behind the data helps in making informed interpretations and avoiding erroneous conclusions. Ultimately, chi-square tests empower analysts to dig beneath the surface of categorical data, revealing hidden connections and informing strategic decisions. Whether it's understanding consumer behavior, evaluating educational programs, or assessing public health interventions, the ability to discern significant associations makes chi-square tests an indispensable tool in the statistical toolkit. By leveraging these tests, researchers and professionals can navigate the complexities of categorical data with confidence, uncovering the patterns that drive meaningful change and innovation. T-tests and Z-tests. You're a wildlife biologist tracking the population of a rare bird species in a sprawling national park. You've set up observation points across various terrains, forests, wetlands, and grasslands, and you're eager to understand if the population differs significantly between these environments. However, your resources are limited, allowing you to collect detailed data from only a handful of observation points. How can you determine whether the differences you observe are genuine or simply the result of random chance? This is where T-tests and Z-tests come into play, acting as your statistical compass to navigate the uncertainties of small and large sample sizes, helping you draw meaningful conclusions from your data. T-tests and Z-tests are fundamental tools in statistics used to compare means and determine if differences between groups are statistically significant. At their core, both tests assess whether the observed differences in sample data reflect true differences in the population or are merely due to random variation. However, the choice between a T-test and a Z-test hinges on the size of your sample and the knowledge you have about the population's variability. Let's delve into the scenario of our wildlife biologist. Suppose at one observation point in the forest, you count an average of 15 birds with a small sample size, say 20 observations. At another point in the wetlands, you observe an average of 18 birds but with only 15 observations. Here, the sample sizes are small, and the variability in bird counts can significantly influence your conclusions. In such cases, the T-test is your go-to method. The T-test is designed to handle small sample sizes by accounting for the extra uncertainty that comes with less data. It adjusts for the fact that estimates of variability, like standard deviation, are less precise when based on smaller samples, providing a more reliable assessment of whether the differences in means are meaningful. Contrast this with a scenario where you have access to extensive data. Suppose you've collected bird counts from hundreds of observation points across the park, with sample sizes soaring to several hundred. With such large samples, the estimates of population variability become much more precise. Here, a z-test becomes appropriate. The z-test leverages the large sample size to assume that the sampling distribution of the mean is normal, even if the underlying population distribution is not perfectly normal. This allows for a more straightforward calculation of the probability that the observed difference in means is due to chance. The distinction between t-tests and z-tests is rooted in the balance between sample size and knowledge of population parameters. The z-test is typically used when you have large samples, usually over 30 observations, and when the population standard deviation is known. In many real-world situations, knowing the exact population standard deviation is rare, making the z-test less commonly applicable outside of controlled environments or theoretical exercises. On the other hand, the t-test is more flexible, requiring only that the sample comes from a normally distributed population or that the sample size is large enough for the central limit theorem to apply, which states that the sampling distribution of the mean becomes approximately normal as the sample size increases. Consider another example in the realm of education. Imagine a teacher wants to compare the average test scores of students from two different teaching methods. If the teacher has only a small class of 10 students for each method, a t-test is essential to account for the limited data and potential variability. The t-test will help determine whether any observed difference in average scores is likely due to the teaching method itself, or just random differences between the small groups. Conversely, if the teacher has access to data from hundreds of students across multiple schools using each teaching method, a z-test might be employed to assess the significance of the difference in average scores, benefiting from the large sample size to provide more precise estimates. Understanding the assumptions behind each test is crucial for accurate application. The t-test assumes that the data are approximately normally distributed, especially important when dealing with small sample sizes. This assumption ensures that the test's reliability is maintained, as the t-distribution is more spread out and accounts for the increased uncertainty in smaller samples. When sample sizes grow, the t-distribution converges to the normal distribution, making the distinction between t-tests and z-tests less pronounced for very large samples. Moreover, there are variations of both t-tests and z-tests tailored to specific research designs. For instance, independent t-tests compare the means of two separate groups, while paired t-tests assess means from the same group at different times or under different conditions. Similarly, z-tests can be adapted for comparing proportions or testing hypotheses about population means when large samples are involved. These variations provide researchers with the flexibility to apply the appropriate test based on their experimental design and data structure. Another key consideration is the presence of outliers or non-normal data distributions. In small samples, outliers can have a disproportionate impact on the mean and increase the standard deviation, potentially skewing the results of a t-test. Researchers must carefully inspect their data, using visual tools like histograms or box plots, and consider transformations or robust statistical methods if the data deviate significantly from normality. In large samples, the influence of outliers is mitigated by the sheer volume of data, making z-tests more resilient to such anomalies. In practical applications, selecting between a t-test and a z-test often involves a preliminary assessment of sample size and the availability of population parameters. Software tools like R, Python SciPy library, SPSS, and Excel make conducting these tests straightforward, automating the calculations and providing p-values that indicate the likelihood of observing the data under the null hypothesis of no difference between groups. These tools also offer diagnostic plots and summary statistics to help researchers verify the assumptions underlying each test, ensuring the validity of their conclusions. Let's revisit our wildlife biologist. Suppose after conducting several observation sessions, the biologist gathers enough data to feel confident in the population estimates. With larger sample sizes, the biologist can switch from using t-tests to z-tests, benefiting from the increased precision in detecting true differences between habitats. This transition exemplifies how understanding the nuances of t-tests and z-tests can enhance the reliability of statistical inferences, guiding better conservation strategies based on robust data analysis. Furthermore, the interpretation of results from t-tests and z-tests requires careful consideration of context and effect sizes. A statistically significant result indicates that the observed difference is unlikely due to chance, but it doesn't necessarily imply practical significance. For example, a t-test might reveal a small but significant difference in bird populations between two habitats. The biologist must then assess whether this difference is ecologically meaningful and warrants changes in conservation practices. Complementary measures, such as confidence intervals and effect size statistics, provide additional insights into the magnitude and importance of the differences detected by these tests. In the broader landscape of statistical analysis, t-tests and z-tests serve as foundational tools that pave the way for more complex inferential methods. They form the basis for understanding concepts like confidence intervals, regression analysis, and ANOVA, which build on the principles of comparing means and assessing variability. Mastery of these tests equips researchers with the skills to tackle a wide range of questions, from experimental design to hypothesis testing, fostering a deeper understanding of the data-driven world. Moreover, the principles underlying t-tests and z-tests extend beyond academia and research, finding applications in everyday decision-making and business strategies. Companies regularly compare customer satisfaction scores, employee performance metrics, or product quality indicators across different departments or time periods. By employing t-tests and z-tests, businesses can make informed decisions based on statistical evidence, optimizing operations and enhancing competitive advantage. Education and training in statistics emphasize the importance of these tests, integrating them into curricula across disciplines to prepare students for real-world analytical challenges. Whether in psychology, economics, biology, or engineering, the ability to conduct and interpret t-tests and z-tests is a critical skill that empowers individuals to extract meaningful insights from data, driving innovation and informed decision-making. As data continues to grow in volume and complexity, the relevance of t-tests and z-tests remains undiminished. They provide a clear and systematic approach to comparing groups, ensuring that conclusions drawn from data are grounded in rigorous statistical reasoning. By choosing the appropriate test based on sample size and population parameters, researchers and professionals can navigate the intricacies of data analysis with confidence, uncovering truths that guide actions and shape our understanding of the world. Ultimately, t-tests and z-tests are more than just statistical procedures. They are essential instruments for distinguishing signal from noise, enabling us to discern genuine patterns amidst the randomness of data. Whether you're comparing the effectiveness of different teaching methods, evaluating the impact of marketing strategies, or assessing environmental interventions, these tests offer a robust framework for making sense of differences and driving evidence-based conclusions. Embracing their strengths and understanding their limitations ensures that your statistical analyses are both accurate and insightful, providing a solid foundation for navigating the ever-evolving landscape of data-driven inquiry. Multivariate statistics. Picture yourself at a bustling farmer's market on a sunny Saturday morning. Stalls overflow with vibrant fruits, vegetables, handmade crafts, and aromatic spices. As you navigate through the crowd, you notice that certain patterns emerge. The popularity of specific produce varies by location within the market, or perhaps the variety of goods sold changes with the time of day. These observations involve multiple factors interacting simultaneously: weather conditions, vendor placement, customer preferences, and more. To make sense of these intricate relationships, statisticians turn to multivariate statistics, a powerful branch of statistics designed to analyze and interpret data involving multiple variables at once. Multivariate statistics is essential in today's data-rich world, where understanding the interplay between various factors can lead to deeper insights and more informed decision-making. Unlike univariate statistics, which examines one variable at a time, or bivariate statistics, which explores the relationship between two variables, multivariate approaches delve into the complexity of three or more variables simultaneously. This capability is crucial across numerous fields, from healthcare and finance to marketing and environmental science, enabling professionals to uncover patterns and relationships that single-variable analyses might overlook. At the heart of multivariate statistics lies the concept of dimensions. Each variable adds a new dimension to the data, creating a multidimensional space where each observation can be represented as a point within that space. Visualizing and interpreting this high-dimensional data can be challenging, but multivariate techniques provide the tools to navigate and make sense of it. For instance, consider a dataset tracking various health metrics, such as blood pressure, cholesterol levels, body mass index, BMI, and age, for a group of individuals. Multivariate analysis allows researchers to explore how these variables interact and influence overall health outcomes, providing a comprehensive view that informs better healthcare strategies. One of the fundamental techniques in multivariate statistics is multiple regression analysis. Imagine a real estate analyst trying to predict house prices based on several factors: location, square footage, number of bedrooms, age of the property, and proximity to schools. Multiple regression enables the analyst to assess the impact of each factor while controlling for the others, determining which variables significantly influence house prices and by how much. This method not only quantifies relationships but also helps in making accurate predictions and informed decisions in complex scenarios where multiple factors are at play. Another pivotal method is principal component analysis (PCA), which serves as a dimensionality reduction tool. Suppose you're a marketer with a vast array of customer data, including age, income, purchase history, website behavior, and social media engagement. PCA can help distill this high-dimensional data into a smaller set of principal components that capture the most significant variance within the dataset. By reducing the number of variables, PCA simplifies the analysis, making it easier to visualize patterns and identify key drivers of customer behavior. This streamlined approach enhances the ability to target marketing efforts more effectively, focusing on the most influential factors. Cluster analysis is yet another essential multivariate technique, used to group similar observations based on multiple characteristics. For example, a healthcare provider might use cluster analysis to categorize patients into distinct groups based on variables such as age, medical history, lifestyle factors, and treatment responses. Identifying these clusters can reveal subpopulations with specific health needs, allowing for more personalized and effective care plans. Similarly, businesses can segment their customer base into distinct groups, tailoring products and services to meet the unique preferences and behaviors of each cluster. Factor analysis delves deeper by uncovering latent variables that explain the correlations among observed variables. Imagine a psychologist studying various aspects of mental health, such as anxiety levels, depression symptoms, stress indicators, and coping mechanisms. Factor analysis can identify underlying factors, like emotional resilience or social support, that influence these observed variables. By revealing these hidden dimensions, researchers gain a more nuanced understanding of the constructs they are studying, leading to more targeted interventions and therapies. Discriminant analysis is another powerful tool used for classification purposes. Suppose a financial institution wants to predict whether loan applicants will default based on multiple financial indicators such as credit score, income, debt-to-income ratio, employment history, and loan amount. Discriminant analysis can build a model that classifies applicants into default or non-default categories by analyzing the combined effect of these variables. This approach enhances the accuracy of predictions, enabling the institution to make more informed lending decisions and manage risk effectively. Canonical correlation analysis explores the relationships between two sets of variables, providing insights into how multiple variables in one set relate to multiple variables in another set. For instance, in educational research, canonical correlation can examine how a set of teaching methods, lectures, interactive sessions, group projects, relates to a set of student outcomes, test scores, engagement levels, retention rates. This holistic analysis captures the multifaceted nature of educational processes, guiding the development of more effective teaching strategies. While multivariate statistics offers powerful tools for analyzing complex data, it also presents challenges that require careful consideration. Multicollinearity, where independent variables are highly correlated, can distort the results of analyses like multiple regression, making it difficult to isolate the individual effect of each variable. Techniques such as variance inflation factor, VIF measurements, variable selection, and dimensionality reduction methods like PCA can help mitigate these issues, ensuring more reliable and interpretable results. Another challenge is the interpretation of results, which demands a solid understanding of the underlying methods and the context of the data. Multivariate analyses can reveal intricate patterns, but translating these patterns into actionable insights requires expertise and domain knowledge. For example, in environmental science, understanding how multiple factors like temperature, precipitation, pollution levels, and land use interact to impact biodiversity involves not just statistical proficiency, but also ecological expertise. Visualization also plays a crucial role in multivariate statistics, helping to make sense of high-dimensional data. Techniques like scatter plot matrices, parallel coordinates plots, and three-dimensional plots enable analysts to explore and communicate the relationships among multiple variables effectively. These visual tools complement statistical methods, providing intuitive insights that support deeper understanding and decision-making. In practical applications, multivariate statistics transforms how we approach problems by providing a comprehensive framework for analysis. In finance, analysts assess how various economic indicators like interest rates, inflation, and unemployment rates jointly impact market trends. In marketing, understanding the combined effect of customer demographics, purchasing behavior, and online engagement can drive more effective targeting and personalized campaigns. In healthcare, studying the interplay between multiple risk factors, treatments, and patient outcomes leads to more effective and personalized medical interventions. The rise of machine learning and artificial intelligence has further amplified the importance of multivariate statistics. Modern algorithms inherently handle multiple variables, enabling the analysis of vast and complex data sets with high dimensionality. Techniques like random forests, support vector machines, and neural networks leverage multivariate principles to recognize patterns and make predictions, driving advancements in areas such as image recognition, natural language processing, and autonomous systems. Educational programs and research initiatives increasingly emphasize multivariate statistics, recognizing its critical role in advancing knowledge across disciplines. By equipping students and researchers with the skills to handle and interpret multiple variables simultaneously, these programs foster a deeper and more nuanced understanding of complex phenomena. This educational focus ensures that the next generation of analysts and scientists can tackle the multifaceted challenges of the modern world with confidence and expertise. Ethical considerations also come into play when applying multivariate statistics. The ability to analyze multiple variables simultaneously can uncover sensitive and potentially intrusive patterns, such as identifying correlations between personal attributes and behaviors. It's imperative to handle such analyses with care, ensuring privacy, consent, and fairness in the interpretation and application of results. Responsible use of multivariate techniques safeguards against misuse and promotes trust in statistical findings. As technology continues to evolve, so too will the tools and methods of multivariate statistics. Innovations in computational power, data storage, and algorithm design will further enhance our ability to analyze and interpret complex data sets. Techniques like deep learning and neural networks, which inherently manage multiple variables, will continue to integrate multivariate principles, driving breakthroughs in areas such as artificial intelligence, bioinformatics, and personalized medicine. Ultimately, multivariate statistics empowers us to see the forest for the trees, capturing the essence of complex interactions among multiple factors. It transforms disparate pieces of information into a cohesive narrative, revealing the underlying structures that shape our world. Whether you're designing a sustainable city, optimizing a business strategy, advancing scientific research, or making informed policy decisions, multivariate statistics provides the analytical prowess to navigate and interpret the intricate tapestry of variables that define our reality. By embracing multivariate approaches, we move beyond simplistic analyses and towards a more sophisticated and accurate understanding of the multifaceted nature of data. This comprehensive perspective not only enhances the quality of our insights, but also equips us to make more informed, effective, and impactful decisions in an increasingly complex and interconnected world. Monte Carlo simulations. If you had to navigate through a maze where each turn is shrouded in uncertainty, how could you determine the most efficient path to your destination? This is the challenge faced by decision-makers in various fields, where outcomes are influenced by numerous unpredictable factors. Enter Monte Carlo simulations, a sophisticated statistical technique that leverages randomness to model and analyze complex systems, enabling informed decision-making despite inherent uncertainties. Monte Carlo simulations are named after the famous Monte Carlo casino in Monaco, reflecting the element of chance that lies at their core. At its essence, this method involves running a large number of simulations to explore the range of possible outcomes in a scenario where uncertainty is a significant factor. By repeatedly sampling from probability distributions of input variables, Monte Carlo simulations generate a spectrum of potential results, providing a comprehensive view of what might happen under different circumstances. Consider a financial analyst tasked with assessing the risk of an investment portfolio. Traditional methods might rely on historical averages and assume that future returns will mirror past performance. However, markets are inherently volatile and influenced by countless variables such as economic indicators, geopolitical events, and investor behavior. By applying Monte Carlo simulations, the analyst can model a wide array of possible market conditions and their impact on the portfolio. This approach not only estimates the range of potential returns, but also quantifies the probability of various outcomes, offering a more nuanced understanding of risk and helping to inform strategic investment decisions. In engineering, designing a bridge requires considering factors like material strength, load distribution, environmental conditions, and construction tolerances. Each of these elements carries its own degree of uncertainty, Monte Carlo simulations allow engineers to input different variables and simulate countless scenarios to evaluate the likelihood of various structural outcomes. This process helps in identifying potential weaknesses, optimizing design parameters, and ensuring that the bridge can withstand a wide range of conditions, thereby enhancing safety and reliability. Healthcare professionals also benefit from Monte Carlo simulations, particularly in treatment planning and resource allocation. For example, in oncology, determining the optimal dosage of a chemotherapy drug involves balancing efficacy against potential side effects. By simulating different dosage levels and patient responses, clinicians can predict the probability of successful outcomes and adverse reactions, guiding personalized treatment plans that maximize benefits while minimizing risks. Similarly, hospital administrators can use simulations to forecast patient inflows, optimize staffing levels, and manage inventory, ensuring that resources are allocated efficiently to meet demand. Environmental scientists utilize Monte Carlo simulations to model complex ecological systems and predict the impact of various interventions. Suppose researchers are studying the effects of climate change on a specific ecosystem, where variables such as temperature, precipitation, species migration, and human activity interact in intricate ways. By simulating thousands of possible future scenarios, scientists can assess the likelihood of different environmental outcomes, identify key drivers of ecosystem changes, and develop strategies to mitigate adverse effects. This probabilistic approach provides a deeper understanding of potential risks and informs policy decisions aimed at preserving biodiversity and ecosystem health. In project management, uncertainty is a constant companion. Whether it's estimating the time required to complete tasks, budgeting for unforeseen expenses, or anticipating potential delays, Monte Carlo simulations offer a robust framework for planning and risk assessment. By inputting various project parameters and running multiple simulations, managers can visualize the range of possible project timelines and costs, identify the most probable challenges, and develop contingency plans. This foresight enhances the ability to deliver projects on time and within budget, even in the face of unexpected obstacles. The versatility of Monte Carlo simulations extends into the realm of supply chain management as well. Companies grappling with demand variability, supplier reliability, and transportation uncertainties can use simulations to model different supply chain configurations and assess their resilience under various conditions. By understanding the probabilities of disruptions and their potential impacts, businesses can design more robust supply chains, implement effective risk mitigation strategies, and ensure continuity of operations even during unforeseen events. One of the remarkable strengths of Monte Carlo simulations is their ability to incorporate a wide range of data and adapt to evolving information. As new data becomes available, simulations can be updated to reflect the latest insights, ensuring that decision-making remains grounded in the most current understanding of the system. This dynamic adaptability is particularly valuable in rapidly changing environments, where static models may quickly become outdated. Moreover, Monte Carlo simulations enhance transparency and communication by providing visual representations of uncertainty and variability. Graphs and charts generated from simulation results can illustrate the probability distributions of outcomes, highlight the most likely scenarios, and identify the tails where extreme events reside. These visual tools make it easier for stakeholders to grasp the implications of uncertainty, fostering more informed and collaborative decision-making processes. Implementing Monte Carlo simulations does require a solid foundation in probability and statistical modeling, as well as access to computational resources capable of handling the extensive calculations involved. However, advancements in software and computing power have made these simulations more accessible, with tools like MATLAB, R, Python's SciPy library, and specialized software such as At Risk and Crystal Ball providing user-friendly platforms for conducting simulations. While Monte Carlo simulations offer powerful insights, it's important to approach them with a critical eye. The quality of the simulation results is heavily dependent on the accuracy of the input data and the appropriateness of the chosen probability distributions. Garbage in, garbage out holds true. If the input assumptions are flawed, the simulation outcomes will be misleading. Therefore, meticulous data collection, validation, and sensitivity analysis are essential steps in the simulation process to ensure reliability and robustness of the results. Furthermore, interpreting the results of Monte Carlo simulations requires a nuanced understanding of probability and statistics. Decision-makers must be able to discern meaningful patterns from the simulated data, assess the significance of various outcomes, and integrate these insights into their strategic frameworks. This demands not only technical proficiency, but also domain-specific knowledge to contextualize the findings and apply them effectively to real-world problems. In sectors like energy, Monte Carlo simulations play a crucial role in forecasting demand, optimizing resource allocation, and planning for future infrastructure needs. Energy companies can simulate different consumption patterns, evaluate the impact of renewable energy sources, and assess the reliability of power grids under various stress conditions. These simulations inform long-term planning and investment decisions, ensuring that energy supply meets demand sustainably and efficiently. In the field of marketing, understanding consumer behavior involves analyzing multiple factors such as demographics, purchasing history, online interactions, and social influences. Monte Carlo simulations enable marketers to model these complex interactions, predict future purchasing trends, and design targeted campaigns that resonate with different customer segments. By simulating various marketing strategies and their potential impacts, businesses can optimize their efforts to maximize engagement and return on investment. Financial modeling is another area where Monte Carlo simulations excel, particularly in portfolio optimization and risk assessment. Investors can simulate the performance of different asset allocations under various market conditions, evaluate the potential returns and risks, and identify the optimal investment strategy that aligns with their risk tolerance and financial goals. This comprehensive approach goes beyond traditional methods, providing a more detailed and probabilistic view of potential investment outcomes. In research and development, Monte Carlo simulations support innovation by allowing scientists and engineers to experiment with different variables and scenarios in a controlled, virtual environment. This accelerates the discovery process, reduces the need for costly and time-consuming physical experiments, and enhances the ability to explore a wider range of possibilities. Whether developing new materials, designing cutting-edge technologies, or testing theoretical models, simulations provide a sandbox for creativity and experimentation. Organizations across industries increasingly recognize the value of Monte Carlo simulations in enhancing their analytical capabilities and driving data-driven strategies. By embracing this technique, businesses and researchers can navigate uncertainty with greater confidence, uncover hidden patterns, and make decisions that are both informed and resilient in the face of variability. The ability to model and simulate complex systems empowers stakeholders to anticipate challenges, seize opportunities, and optimize outcomes in an ever-changing world. Monte Carlo simulations embody the intersection of randomness and structured analysis, transforming uncertainty into actionable insights. By systematically exploring the myriad possibilities inherent in complex systems, this technique provides a robust foundation for making informed decisions, managing risks, and optimizing performance across a diverse array of applications. As the landscape of data continues to evolve, the role of Monte Carlo simulations in powering intelligent decision-making is set to become even more pivotal, driving advancements and fostering innovation in an increasingly data-driven society. Markov chains. Given a sequence of events where each event depends solely on the immediate preceding one, how can we predict what comes next with any degree of accuracy? This scenario encapsulates the essence of Markov chains, a foundational concept in probability theory and statistics that models stochastic processes where the future state depends only on the current state, not on the sequence of events that preceded it. Markov chains are characterized by a finite or countable set of states and the probabilities of transitioning from one state to another. This property, known as the Markov property or memorylessness, simplifies the complexity of predicting future states by focusing solely on the present. For instance, consider a simple weather system with 3 states: sunny, cloudy, and rainy. The likelihood of tomorrow being sunny depends only on today's weather, not on how we arrived at today's conditions. By analyzing historical weather data, we can estimate the transition probabilities between these states and use them to forecast future weather patterns. One of the most intuitive applications of Markov chains is in board games like Monopoly. Each square on the board represents a state, and the roll of the dice determines the transition from one state to another. Over time, certain squares become more frequently visited based on their connectivity and the rules of the game, such as the jail or go-to-jail squares. By modeling the game as a Markov chain, players and analysts can understand the long-term distribution of where players are likely to land, which can inform strategies and game design. In the realm of technology, Markov chains underpin the functionality of search engines and recommendation systems. Google's PageRank algorithm, for example, models the web as a vast Markov chain where each web page is a state, and links between pages represent transitions with certain probabilities. This approach helps determine the importance and ranking of web pages based on the likelihood of transitioning from one page to another, ultimately influencing search results and user navigation. Language processing also leverages Markov chains to model the probability of sequences of words. In text generation or speech recognition, the likelihood of a particular word appearing next in a sentence is based on the current word, enabling systems to predict and generate coherent and contextually relevant text. This application is fundamental in technologies like autocomplete features in search engines and predictive text in smartphones. Financial markets utilize Markov chains to model stock prices and market behaviors. While markets are influenced by a myriad of factors, the Markov property allows analysts to focus on the current state of the market to predict future movements. By estimating transition probabilities based on historical price data, investors can assess the likelihood of various market scenarios, aiding in portfolio management and risk assessment. Healthcare and genetics also benefit from Markov chains in modeling patient health states and genetic sequences. For example, patient progression through different health states, such as healthy, diagnosed, treated, and recovered, can be modeled as a Markov chain, helping medical professionals predict outcomes and optimize treatment plans. In genetics, the sequence of nucleotides in DNA can be analyzed using Markov chains to identify patterns and predict genetic variations. Another fascinating application is in ecology, where Markov chains model animal movement and population dynamics. By understanding the probabilities of animals moving between different habitats or states, e.g., breeding, feeding, migrating, ecologists can predict population trends and assess the impact of environmental changes on wildlife. Implementing Markov chains involves defining the states of the system and estimating the transition probabilities between these states. These probabilities are often derived from empirical data through methods like maximum likelihood estimation or Bayesian inference. Once the model is established, it can be used to simulate future states, analyze steady-state behaviors, and evaluate the long-term properties of the system. Advanced variations of Markov chains, such as hidden Markov models, HMMs, extend the basic concept by allowing the states to be partially observable. In HMMS, the system transitions between hidden states that emit observable signals, making them particularly useful in fields like speech recognition and bioinformatics, where the underlying processes are not directly observable but can be inferred from measurable data. Despite their simplicity, Markov chains offer a robust framework for modeling a wide array of real-world phenomena where the future is conditionally independent of the past, given the present. Their versatility and mathematical elegance make them indispensable tools in both theoretical research and practical applications, enabling us to navigate and predict complex systems with a foundation of probabilistic reasoning. Non-parametric statistics. Should you encounter data that defies the neat assumptions of normality, equal variances, or linear relationships, non-parametric statistics become your invaluable allies. These methods offer robust alternatives to traditional parametric tests, providing flexibility and reliability when dealing with irregular, skewed, or ordinal data. Whether you're analyzing survey responses, biological measurements, or any data set that doesn't fit the conventional molds, non-parametric techniques empower you to extract meaningful insights without being constrained by stringent statistical assumptions. One of the primary advantages of non-parametric statistics is their minimal reliance on data distribution. Unlike parametric tests, which often require data to follow a normal distribution and assume homogeneity of variances, non-parametric methods make fewer assumptions about the underlying population. This makes them particularly useful in real-world scenarios where data often deviate from ideal conditions due to outliers, skewness, or limited sample sizes. For instance, consider a researcher studying customer satisfaction levels using an ordinal scale, e.g., rating from 1 to 5. Traditional parametric tests might struggle with such data because the intervals between ratings are not necessarily equal. Instead, non-parametric tests like the Mann-Whitney U-test or the Wilcoxon signed rank test can effectively compare medians between groups without assuming equal intervals, providing a more accurate reflection of customer sentiments. Another common application is in medical research, where patient outcomes may not follow a normal distribution. Suppose a clinical trial measures the improvement in symptoms using a nonlinear scale. In this case, the Kruskal-Wallis H-test offers a way to compare multiple treatment groups without the need for normally distributed data, ensuring that the conclusions drawn are based on the actual data characteristics rather than imposed assumptions. Non-parametric methods also excel in handling small sample sizes, where the power of parametric tests may be limited. When working with limited data, techniques such as bootstrapping can be employed to estimate confidence intervals and assess the significance of findings without relying on large sample approximations. This is particularly beneficial in exploratory studies or pilot experiments where data collection may be constrained by resources or feasibility. Beyond hypothesis testing, non-parametric statistics encompass a variety of tools for correlation and association. Spearman's rank correlation coefficient, for example, measures the strength and direction of association between two ranked variables, making it suitable for assessing relationships that are monotonic but not necessarily linear. This is invaluable in fields like psychology and education, where relationships between variables often exhibit complex patterns that parametric methods might overlook. In addition to tests, non-parametric methods include robust measures of central tendency and dispersion. The median serves as a reliable measure of central tendency when data are skewed, providing a better summary than the mean, which can be heavily influenced by outliers. Similarly, the interquartile range offers a robust measure of variability, capturing the spread of the middle 50% of the data without being affected by extreme values. Moreover, non-parametric techniques extend to advanced modeling and machine learning. Algorithms like decision trees and random forests inherently rely on non-parametric principles, making them highly adaptable to various data types and structures. These models do not assume a specific form for the relationship between variables, allowing them to capture complex interactions and nonlinearities that parametric models might miss. Implementing non-parametric statistics often involves leveraging specialized software and programming libraries. Tools such as R, Python's SciPy, and Stats Models libraries, and statistical packages like SPSS and SAS provide comprehensive support for conducting non-parametric tests and analyses. These tools facilitate the application of non-parametric methods, enabling researchers and analysts to focus on interpreting results rather than grappling with computational complexities. Despite their strengths, non-parametric methods are not without limitations. They may offer less statistical power compared to parametric tests when parametric assumptions are met, meaning that they might require larger sample sizes to detect significant effects. Additionally, non-parametric tests often provide less detailed information about the nature and magnitude of relationships between variables, focusing instead on the presence or absence of differences or associations. To maximize the effectiveness of non-parametric statistics, it is essential to complement them with thoughtful data exploration and visualization. Techniques such as box plots, histograms, and scatter plots can help identify the appropriate non-parametric methods to apply and ensure that the chosen techniques align with the data's characteristics and the research objectives. In practice, the decision to use non-parametric statistics should be guided by the data's nature and the specific research questions at hand. When data violate parametric assumptions, are ordinal or nominal, or involve small sample sizes, non-parametric methods provide a reliable and flexible framework for analysis. By embracing these techniques, analysts and researchers can navigate the complexities of real-world data, uncovering insights that drive informed decisions and meaningful advancements across diverse fields. Machine learning and statistics. If you were developing a recommendation system for an online streaming service, how would you ensure that users receive personalized suggestions tailored to their unique tastes? The answer lies in the intricate dance between machine learning and statistics, where probability serves as the cornerstone of artificial intelligence, AI. By leveraging probabilistic models, AI systems can interpret vast amounts of data, make informed predictions, and adapt to changing patterns, ultimately enhancing user experiences and driving innovation across various industries. At the heart of machine learning is the ability to learn from data, and statistics provides the foundational framework for understanding and modeling this data. Probability, a key component of statistics, quantifies uncertainty and enables AI models to make predictions based on incomplete or noisy information. For instance, in natural language processing, NLP, probabilistic models help AI systems understand and generate human language by estimating the likelihood of word sequences, allowing for more accurate translations, sentiment analysis, and conversational agents. One of the fundamental ways AI utilizes probability is through probabilistic graphical models. These models represent complex relationships between variables using graphs, where nodes denote variables and edges signify probabilistic dependencies. By capturing the conditional dependencies among multiple variables, probabilistic graphical models enable AI systems to reason about uncertainties and make predictions based on the interplay of various factors. This is particularly useful in areas like computer vision, where understanding the context and relationships between different visual elements is crucial for tasks such as object recognition and scene understanding. Ensemble methods in machine learning also harness probability to improve predictive performance. Techniques like random forests and gradient boosting combine multiple models to produce more accurate and robust predictions. Each individual model within an ensemble makes predictions based on different subsets of data or features, and the final prediction is typically determined by aggregating these individual probabilities. This approach reduces the risk of overfitting and enhances the model's ability to generalize to new, unseen data, making it a powerful tool for applications ranging from fraud detection to personalized marketing. In the realm of deep learning, probabilistic approaches play a vital role in enhancing model reliability and interpretability. For example, dropout is a regularization technique that introduces randomness during training by temporarily dropping out a subset of neurons in a neural network. This probabilistic method helps prevent overfitting by ensuring that the network does not become overly reliant on any single neuron, promoting the development of more generalized and resilient models. Additionally, techniques like variational inference allow deep learning models to estimate uncertainty in their predictions, providing valuable insights into the confidence levels of AI-driven decisions. Probabilistic clustering is another area where machine learning and statistics converge to unlock meaningful patterns in data. Unlike traditional clustering methods that assign data points to fixed groups, probabilistic clustering algorithms such as Gaussian mixture models, GMMs, estimate the probability that each data point belongs to each cluster. This approach accommodates the inherent uncertainty and overlap between clusters, offering a more flexible and nuanced understanding of data structures. Applications of probabilistic clustering span diverse fields, including image segmentation, customer segmentation, and anomaly detection, where recognizing subtle variations within data is essential. Bayesian optimization is a technique that leverages probability to efficiently search for optimal solutions in complex and high-dimensional spaces. Commonly used in hyperparameter tuning for machine learning models, Bayesian optimization builds a probabilistic model of the objective function and uses it to select the most promising parameters to evaluate next. By balancing exploration and exploitation, this method reduces the number of required evaluations, saving computational resources and accelerating the model development process. This probabilistic approach is invaluable in scenarios where evaluating the objective function is costly or time-consuming, such as in automated machine learning, AutoML, and experimental design. In the field of reinforcement learning, probability underpins the decision-making processes of agents interacting with dynamic environments. Agents use probabilistic models to estimate the expected rewards of different actions, allowing them to make choices that maximize long-term benefits. Techniques like policy gradients and Q-learning incorporate probabilistic elements to handle the uncertainty and variability of real-world environments, enabling agents to adapt and learn optimal strategies over time. This probabilistic foundation is critical for applications such as robotics, autonomous vehicles, and game playing, where agents must navigate and respond to ever-changing conditions. Probabilistic programming is an emerging paradigm that integrates probability theory directly into programming languages, facilitating the creation of complex statistical models and machine learning algorithms. By allowing developers to define models that incorporate uncertainty and probabilistic dependencies, probabilistic programming languages like Stan, PyMC, and TensorFlow probability simplify the implementation of sophisticated AI systems. This approach accelerates the development of models that can reason under uncertainty, making it easier to build applications that require robust and flexible probabilistic reasoning, such as predictive maintenance, personalized medicine, and financial forecasting. Moreover, uncertainty quantification is a critical aspect of AI that relies heavily on probability. In applications like autonomous driving, medical diagnostics, and financial risk assessment, understanding the uncertainty associated with AI predictions is paramount for making safe and reliable decisions. Techniques such as Monte Carlo dropout, Bayesian neural networks and ensemble learning provide ways to estimate and interpret the uncertainty in AI models, ensuring that decisions are made with a clear understanding of potential risks and confidence levels. The synergy between machine learning and statistics, particularly through the use of probability, enables AI to handle complexity, adapt to new information, and make informed predictions in uncertain environments. By grounding AI models in statistical theory, probability empowers these systems to interpret intricate data patterns, manage variability, and enhance decision-making processes across a multitude of applications. This integration not only improves the accuracy and reliability of AI systems, but also fosters innovation and advancement in fields as diverse as healthcare, finance, technology, and beyond. Embracing probabilistic methods within machine learning transforms raw data into actionable insights, allowing AI to navigate the uncertainties of the real world with precision and adaptability. As AI continues to evolve, the interplay between machine learning and statistical probability will remain pivotal, driving the development of smarter, more resilient, and more trustworthy artificial intelligence that can effectively address the complexities and challenges of an increasingly data-driven society. Big data and statistical trends. Every day, the volume, velocity, and variety of data generated across the globe reach unprecedented levels. From social media interactions and online transactions to sensor readings and genomic sequences, the deluge of information presents both immense opportunities and formidable challenges. In this landscape, statistics emerges as a crucial tool for making sense of big data, uncovering hidden patterns, and driving informed decision-making in the modern world. Big data refers to datasets that are so large and complex that traditional data processing techniques are inadequate. The three defining characteristics of big data, volume, velocity, and variety, demand advanced statistical methods to extract meaningful insights. Statistics provides the framework for designing experiments, analyzing data, and interpreting results, ensuring that the vast streams of information can be transformed into actionable knowledge. One of the primary roles of statistics in the era of big data is data summarization and visualization. With billions of data points, identifying key trends and patterns at a glance is essential. Statistical techniques such as clustering, dimensionality reduction, and principal component analysis help distill complex datasets into understandable formats. Visualization tools, powered by statistical principles, enable analysts to create intuitive charts, graphs, and dashboards that highlight significant trends and anomalies, facilitating quick and effective decision-making. Predictive analytics is another area where statistics plays a pivotal role. By applying statistical models to historical data, organizations can forecast future events with a degree of confidence. For example, retailers use predictive analytics to anticipate customer demand, optimize inventory levels, and personalize marketing campaigns. Financial institutions leverage these techniques to assess credit risk, detect fraudulent transactions, and forecast market movements. The ability to predict outcomes based on data-driven models enhances strategic planning and operational efficiency across various industries. In addition to prediction, statistics is essential for descriptive analytics, which involves summarizing and interpreting data to understand what has happened in the past. Techniques such as regression analysis, time series analysis, and hypothesis testing allow businesses to evaluate performance metrics, identify causal relationships, and measure the impact of interventions. Descriptive analytics provides the foundational knowledge needed to build more sophisticated models and strategies tailored to specific business objectives. Machine learning, a subset of artificial intelligence, heavily relies on statistical foundations to develop algorithms that can learn from and make predictions based on data. Statistical methods underpin many machine learning techniques, from supervised learning algorithms like linear and logistic regression to unsupervised methods such as k-means clustering and hierarchical clustering. By integrating statistical principles with computational power, machine learning models can handle the scale and complexity of big data, enabling applications like recommendation systems, image and speech recognition, and autonomous vehicles. The integration of statistical quality control in manufacturing and production processes exemplifies how statistics ensures efficiency and reliability in the modern world. By monitoring and analyzing production data in real time, statistical methods help detect defects, minimize variability, and maintain high standards of quality. This proactive approach not only reduces costs associated with waste and rework, but also enhances customer satisfaction by delivering consistent and superior products. In the realm of healthcare, statistics is instrumental in managing and analyzing large-scale health data to improve patient outcomes and operational efficiency. Electronic health records, medical imaging, and genomic data generate vast amounts of information that can be harnessed to identify disease patterns, optimize treatment protocols, and personalize patient care. Statistical models aid in predicting disease outbreaks, evaluating the effectiveness of new treatments, and managing healthcare resources more effectively, ultimately contributing to better public health and well-being. Social sciences also benefit immensely from the application of statistics to big data. Researchers analyze social media trends, consumer behavior, and demographic information to understand societal changes, influence policy-making, and drive social interventions. Statistical techniques enable the examination of complex social phenomena, revealing insights into human behavior, cultural shifts, and economic dynamics that inform both academic research and practical solutions to societal challenges. Moreover, the role of data ethics and privacy in big data analytics underscores the importance of statistical methods in ensuring responsible data usage. Statistics not only provides the tools for analyzing data, but also guides the development of frameworks for data governance, ensuring that data is used ethically and that individual privacy is protected. Techniques such as anonymization, differential privacy, and secure multi-party computation are rooted in statistical principles, balancing the need for data-driven insights with the imperative to safeguard personal information. As the landscape of big data continues to evolve, the synergy between statistics and emerging technologies will drive further advancements. Innovations in real-time analytics, edge computing, and Internet of Things, IoT, will expand the capabilities of statistical methods, enabling more dynamic and responsive data analysis. The continuous development of statistical methodologies will ensure that as data grows in complexity and scale, our ability to interpret and utilize it remains robust and effective. In sectors like energy, transportation, and environmental management, statistics facilitates the optimization of resources, the improvement of sustainability practices, and the mitigation of risks. For instance, energy companies use statistical models to forecast demand, optimize grid operations, and integrate renewable energy sources more efficiently. Transportation planners analyze traffic patterns and public transit usage to enhance mobility and reduce congestion. Environmental scientists employ statistical techniques to monitor ecosystem health, predict the impacts of climate change, and develop strategies for conservation and sustainability. Educational institutions are also embracing the power of statistics and big data to enhance learning outcomes and operational efficiency. By analyzing student performance data, institutions can identify at-risk students, tailor educational programs, and improve resource allocation. Administrative functions such as admissions, enrollment forecasting, and alumni engagement benefit from data-driven insights, leading to more effective and strategic decision-making processes. The collaborative nature of big data analytics further amplifies the role of statistics. Interdisciplinary teams, comprising statisticians, data scientists, domain experts, and technologists, work together to tackle complex problems, leveraging their collective expertise to extract maximum value from data. This collaborative approach fosters innovation, drives research advancements, and ensures that statistical insights are effectively translated into practical solutions. In summary, statistics is the linchpin that holds together the vast and intricate world of big data, providing the tools and methodologies necessary to transform raw information into valuable insights. From predictive analytics and machine learning to quality control and healthcare advancements, the role of statistics in the modern world is both foundational and transformative. As data continues to permeate every aspect of our lives, the importance of statistical expertise will only grow, empowering us to navigate the complexities of the digital age with clarity, precision, and informed judgment. Set theory and probability. Set theory provides the fundamental language through which probability and, by extension, statistics communicate and operate. By defining and manipulating collections of objects, set theory lays the groundwork for understanding how probabilities are assigned, how events interact, and how complex statistical concepts are structured. Without set theory, the precise and logical framework necessary for rigorous statistical analysis would be unattainable. At its core, set theory deals with the study of sets, which are simply well-defined collections of distinct objects. These objects, known as elements or members, can be anything from numbers and symbols to more abstract entities like events or outcomes. In the realm of probability, sets are used to represent events, specific outcomes or combinations of outcomes within a larger experiment or process. For example, when flipping a coin, the set of possible outcomes is heads-tails. If we consider rolling a die, the set of possible outcomes is 1, 2, 3, 4, 5, 6, 6. One of the most powerful aspects of set theory and probability is its ability to define and manipulate events through operations such as union, intersection, and complement. The union of two sets combines all elements from both sets, representing the event that either one or the other occurs. The intersection identifies elements common to both sets, corresponding to the event that both occur simultaneously. The complement of a set consists of all elements not in the set, representing the event that a particular outcome does not occur. These operations allow statisticians to build complex event structures from simpler ones, facilitating nuanced probability assessments. Probability itself is deeply intertwined with set theory through the concept of a probability space, which consists of three components: a sample space, events, and a probability measure. The sample space is the set of all possible outcomes of an experiment. Events are subsets of the sample space, representing specific outcomes or groups of outcomes. The probability measure assigns a numerical value between 0 and 1 to each event, quantifying the likelihood of that event occurring. This formalization ensures that probabilities adhere to logical consistency and mathematical rigor, essential for valid statistical inferences. One of the foundational principles derived from set theory and probability is the axiom of additivity. This principle states that the probability of the union of mutually exclusive events is equal to the sum of their individual probabilities. In other words, if two events cannot occur simultaneously, the probability that either one occurs is simply the sum of their probabilities. This axiom is crucial for calculating probabilities in scenarios where multiple independent events are involved, ensuring that combined probabilities are accurately represented. Furthermore, set theory facilitates the understanding of conditional probability, which assesses the likelihood of an event occurring, given that another event has already occurred. Conditional probability is defined using the intersection of sets, where the probability of event A given event B is the probability of both A and B occurring, divided by the probability of B. This concept is fundamental in statistical analyses that involve dependencies between variables, such as in Bayesian statistics or in assessing the relationship between risk factors and outcomes in medical studies. Another significant contribution of set theory to probability is the concept of independence. Two events are considered independent if the occurrence of one does not affect the probability of the other. Mathematically, this is expressed by the probability of the intersection of the two events being equal to the product of their individual probabilities. Independence is a key assumption in many statistical models and tests, allowing for the simplification of complex probability calculations and the development of robust analytical methods. Beyond these basic concepts, set theory underpins more advanced probability topics such as random variables, probability distributions, and expected values. A random variable is a function that assigns a numerical value to each outcome in the sample space, effectively mapping events to numbers. Probability distributions describe how probabilities are allocated across the possible values of a random variable, providing a complete characterization of its behavior. The expected value or mean of a random variable is a weighted average of all possible values, where the weights are the probabilities assigned to each value. These concepts are essential for summarizing data, making predictions, and conducting hypothesis tests in statistics. In practical applications, the synergy between set theory and probability manifests in various statistical techniques and methodologies. For instance, in hypothesis testing, set theory is used to define null and alternative hypotheses as sets of possible parameter values. The construction of confidence intervals relies on understanding the probability distributions of estimators, which are grounded in set theoretic definitions of events and their probabilities. Additionally, regression analysis, classification, and clustering, all cornerstone techniques in statistical analysis and machine learning, are built upon the principles of set theory and probability, enabling the modeling and interpretation of complex data relationships. Moreover, set theory aids in the visualization and communication of statistical concepts. Venn diagrams, which depict sets and their relationships through overlapping circles, are a classic tool for illustrating probabilities, intersections, and unions of events. These visual representations make abstract probability concepts more tangible and easier to comprehend, facilitating better understanding and collaboration among statisticians, researchers, and stakeholders. In the modern world, where data-driven decision-making is paramount, the interplay between set theory and probability ensures that statistical analyses are both precise and reliable. From designing experiments and surveys to analyzing vast datasets in big data environments, the mathematical backbone provided by set theory and probability equips statisticians with the tools needed to extract meaningful insights, assess risks, and inform strategic actions. By embracing the foundational principles of set theory and probability, statisticians can navigate the complexities of data with confidence and clarity. This robust mathematical framework not only supports the integrity of statistical methods, but also drives innovation and advancement across diverse fields such as finance, healthcare, engineering, and social sciences. As our world becomes increasingly reliant on data, the role of set theory and probability in shaping and guiding statistical practice remains indispensable, underpinning the quest for knowledge and the pursuit of informed, evidence-based decisions. Linear algebra in statistics. For anyone delving into the world of statistics, matrices might initially seem like abstract mathematical constructs reserved for advanced courses. However, they are, in fact, the unsung heroes that power a vast array of statistical methods and applications. From simplifying complex calculations to enabling sophisticated modeling techniques, linear algebra and specifically matrices, are integral to understanding and performing modern statistical analysis. At its core, linear algebra deals with vectors and matrices, which are essentially organized collections of numbers. In statistics, matrices provide a structured way to handle and manipulate large data sets efficiently. Imagine you have a data set with hundreds of observations and dozens of variables. Representing this data as a matrix allows statisticians to perform operations like transformations, scaling, and rotations systematically, facilitating easier analysis and interpretation. One of the most fundamental uses of matrices in statistics is in multivariate analysis, where multiple variables are analyzed simultaneously. Techniques such as multiple regression, principal component analysis, PCA, and factor analysis rely heavily on matrix operations. For example, in multiple regression, the relationship between several independent variables and a dependent variable is modeled using matrix multiplication and inversion, streamlining the process of estimating coefficients and assessing their significance. Principal component analysis, PCA, is another powerful statistical tool that leverages matrices to reduce the dimensionality of data. By transforming the original variables into a new set of uncorrelated variables, principal components, PCA simplifies the dataset while retaining most of its variability. This transformation is achieved through matrix decomposition techniques like eigenvalue decomposition or singular value decomposition, SVD, which break down the data matrix into its constituent parts, revealing the underlying structure and patterns. In the realm of machine learning, matrices are indispensable for building and training models. Algorithms such as linear discriminant analysis, LDA, support vector machines, SVM, and neural networks utilize matrices to represent and process input data, weights, and activations. For instance, in neural networks, the connections between neurons are modeled as matrices of weights, and matrix multiplication is used to compute the outputs of each layer, enabling the network to learn complex relationships within the data. Time series analysis also benefits from matrix representations, especially when dealing with multiple interrelated time series. Techniques like vector autoregression, VAR, model the dynamic relationships between multiple time-dependent variables using matrices to capture the interactions and dependencies over time. This matrix-based approach allows for more accurate forecasting and understanding of how variables influence each other in a temporal context. Beyond these applications, matrices facilitate efficient computation and data manipulation, which are crucial in handling big data and high-dimensional data sets. Modern statistical software and programming languages, such as R, Python, with libraries like NumPy and Pandas, and MATLAB, are optimized for matrix operations, enabling statisticians to perform complex analyses quickly and effectively. This computational efficiency is essential for tasks like bootstrapping, permutation testing, and Monte Carlo simulations, where repeated calculations on large data sets are required. Covariance and correlation matrices are foundational in understanding the relationships between variables. These matrices summarize how variables covary or correlate with one another, providing insights into the underlying structure of the data. Analyzing these matrices helps identify patterns, such as clusters of highly correlated variables, which can inform feature selection and dimensionality reduction strategies in various statistical and machine learning applications. In experimental design, matrices play a critical role in structuring and analyzing data from factorial experiments, where multiple factors and their interactions are studied simultaneously. The use of design matrices allows researchers to systematically arrange experimental conditions and apply linear models to assess the main effects and interactions, ensuring that the analysis is both comprehensive and interpretable. Moreover, matrices underpin Bayesian statistics, where they are used to represent and manipulate prior distributions, likelihoods, and posterior distributions. In Bayesian linear regression, for instance, matrices are used to express the relationship between predictors and responses, facilitating the calculation of posterior estimates and credible intervals through matrix-based computations. The versatility of matrices in statistics extends to graphical models and network analysis, where they represent connections and dependencies between variables or nodes. Adjacency matrices, for example, are used to depict relationships in social networks, biological networks, and communication systems, enabling the application of statistical techniques to analyze and interpret these complex structures. Educationally, mastering linear algebra and matrix operations equips statisticians with the tools to tackle a wide range of analytical challenges. Understanding how to manipulate and interpret matrices fosters a deeper comprehension of statistical concepts and enhances the ability to develop and apply advanced models effectively. In essence, matrices are the mathematical backbone that support and enhance statistical analysis. Their ability to organize, simplify, and facilitate complex computations makes them indispensable in both theoretical and applied statistics, whether it's uncovering hidden patterns in high-dimensional data, optimizing machine learning algorithms, or designing robust experiments. Linear algebra and matrices are fundamental to the advancement and efficacy of statistical practices in the modern world. Calculus and optimization. Get ready to unlock the mathematical secrets behind finding the most efficient and effective solutions in a multitude of fields. Calculus and optimization form a dynamic duo in statistics, engineering, economics, and beyond, enabling us to identify optimal strategies, minimize costs, and maximize benefits with precision and rigor. By leveraging the principles of calculus, optimization techniques delve into the heart of complex problems, providing the tools needed to navigate and solve them systematically. At its core, calculus involves the study of change in motion through derivatives and integrals. In the context of optimization, derivatives play a crucial role in identifying points where a function reaches its maximum or minimum values. For instance, in statistical modeling, optimizing a likelihood function to estimate parameters involves taking derivatives to find the points where the function's slope is zero, indicating potential maxima or minima. This process ensures that models are fitted as accurately as possible to the observed data, enhancing their predictive power and reliability. Optimization extends beyond simple maximization or minimization tasks, encompassing a wide range of techniques designed to find the best possible solution under given constraints. In linear regression, for example, the goal is to minimize the sum of squared residuals between observed and predicted values. This is achieved through methods like least squares optimization, which systematically adjusts model parameters to achieve the lowest possible error. Such optimization ensures that the statistical models are both accurate and efficient, providing meaningful insights from complex data sets. One of the most widely used optimization algorithms in machine learning and statistics is gradient descent. This iterative method uses calculus to update model parameters in the direction that most rapidly decreases the loss function. By calculating the gradient, the vector of partial derivatives, of the loss function with respect to each parameter, gradient descent moves step by step towards the optimal solution. This technique is fundamental in training neural networks, where millions of parameters must be fine-tuned to achieve high levels of accuracy and performance. In more advanced applications, constrained optimization techniques come into play, where solutions must satisfy certain conditions or restrictions. Lagrange multipliers are a powerful tool in this context, allowing statisticians and engineers to find the extrema of functions subject to equality constraints. For example, In portfolio optimization within finance, investors seek to maximize expected returns while adhering to risk constraints. By applying constrained optimization, it's possible to determine the optimal asset allocation that balances these competing objectives effectively. Nonlinear optimization addresses scenarios where the objective function or the constraints are not linear, adding a layer of complexity that requires sophisticated calculus-based methods. Techniques such as Newton-Raphson and quasi-Newton methods utilize second-order derivatives to achieve faster convergence rates compared to first-order methods like gradient descent. These methods are essential in fields like bioinformatics and operations research, where nonlinear relationships are commonplace and require precise optimization strategies to solve intricate problems. Another critical area where calculus and optimization intersect is in Bayesian statistics, particularly in the optimization of posterior distributions. Techniques like variational inference employ optimization to approximate complex posterior distributions, making Bayesian methods computationally feasible for large-scale problems. By minimizing the divergence between the true posterior and the approximating distribution, variational inference provides a scalable solution for probabilistic modeling and inference. Dynamic programming is yet another optimization strategy that breaks down complex problems into simpler subproblems, solving each one just once and storing their solutions. This approach is invaluable in scenarios like time series forecasting and resource allocation, where decisions at one stage affect outcomes in subsequent stages. By systematically optimizing each step, dynamic programming ensures that the overall solution is both optimal and computationally efficient. In the realm of data science, optimization techniques are integral to feature selection, hyperparameter tuning, and model evaluation. For example, regularization methods like lasso and ridge regression add penalty terms to the loss function, promoting simpler models that generalize better to new data. These regularization terms are optimized alongside the model parameters, striking a balance between model complexity and predictive accuracy. Simulated annealing and genetic algorithms represent optimization techniques inspired by natural processes such as metallurgy and biological evolution. These heuristic methods are particularly useful for solving complex, high-dimensional problems where traditional calculus-based optimization may falter. By exploring a broader search space and avoiding local minima, these algorithms enhance the likelihood of finding globally optimal solutions in challenging scenarios. The synergy between calculus and optimization extends to control theory, where systems are regulated to achieve desired behaviors. By modeling system dynamics with differential equations and optimizing control inputs, engineers can design controllers that maintain stability, maximize performance, and respond adaptively to changing conditions. This application is crucial in fields like aerospace, robotics, and automated manufacturing where precise control is paramount. Educationally, a strong foundation in calculus and optimization equips statisticians and data scientists with the analytical skills needed to tackle a wide array of problems. Courses in mathematical optimization, numerical methods, and advanced calculus provide the theoretical underpinnings necessary for understanding and applying these techniques effectively. Practical experience with software tools such as MATLAB, R, Python, with libraries like SciPy and TensorFlow, and specialized optimization packages further enhances one's ability to implement and solve real-world problems. The importance of calculus and optimization in statistics and beyond cannot be overstated. These mathematical disciplines provide the essential tools for navigating complexity, ensuring that solutions are not only feasible but also optimal. Whether it's refining a predictive model, designing an efficient system, or making strategic business decisions, the principles of calculus and optimization guide us towards the best possible outcomes, transforming data and ideas into actionable, impactful results. Game theory and decision-making. Games are more than just entertainment. They embody the essence of strategic interaction, where players make decisions to maximize their outcomes based on the actions of others. This intricate dance of choices and consequences is at the heart of game theory, a branch of mathematics that analyzes competitive situations where the outcome for each participant depends on the actions of all involved. By modeling these interactions, game theory provides profound insights into decision-making processes, influencing fields as diverse as economics, political science, biology, and artificial intelligence. At its core, game theory examines how rational agents make decisions in environments where their choices affect one another. Unlike traditional statistical methods that often focus on independent variables, game theory acknowledges the interdependence of players' strategies, making it a powerful tool for understanding and predicting behavior in competitive and cooperative scenarios. Whether it's businesses competing in a market, countries negotiating treaties, or animals vying for resources, game theory offers a structured framework to analyze and navigate these complex interactions. One of the foundational concepts in game theory is the Nash equilibrium, named after mathematician John Nash. A Nash equilibrium occurs when each player in a game selects a strategy that maximizes their own payoff, given the strategies chosen by the other players. In this state, no player has an incentive to unilaterally change their strategy, as doing so would not yield a better outcome. This concept is pivotal in predicting stable outcomes in competitive environments. For example, in pricing strategies among competing firms, a Nash equilibrium can indicate a point where no single company can improve its market position by altering its prices alone. Zero-sum games represent a class of games where one player's gain is exactly balanced by the losses of others. Chess and poker are classic examples, where the success of one player directly results in the failure of another. In such games, strategies are often about anticipating and countering the opponent's moves to ensure victory. Analyzing zero-sum games helps in developing optimal strategies that account for the worst-case scenarios, ensuring that a player can at least achieve a satisfactory outcome, regardless of the opponent's actions. Conversely, non-zero-sum games allow for outcomes where all players can benefit or suffer simultaneously. The Prisoner's Dilemma is a quintessential non-zero-sum game that illustrates the tension between individual rationality and collective benefit. In this scenario, two prisoners must decide whether to cooperate with each other or betray the other. The dilemma highlights how rational decisions based on self-interest can lead to suboptimal outcomes for all parties involved. Understanding such dynamics is crucial in areas like international relations, where cooperation between nations can lead to mutual benefits, but distrust and competitive incentives may hinder collective progress. Cooperative game theory explores how players can form coalitions and agreements to achieve better outcomes collectively. Unlike non-cooperative games, where binding agreements are not possible, cooperative games assume that players can negotiate and enforce contracts. This aspect of game theory is instrumental in studying alliances, mergers, and partnerships in business, as well as coalition building in political settings. Techniques like the Shapley value help in fairly distributing the gains from cooperation among the participants, ensuring that each player's contribution is appropriately recognized. Evolutionary game theory extends traditional game theory by incorporating dynamics of strategy changes over time, influenced by factors such as reproduction, mutation, and selection. This approach is particularly useful in biology for understanding the evolution of behaviors and strategies in populations of organisms. For example, the evolution of altruistic behavior in animals can be studied through evolutionary game models, shedding light on how cooperative strategies can emerge and stabilize in a competitive environment. In the realm of economics, game theory is indispensable for analyzing market structures, auction designs, and bargaining scenarios. It provides the tools to model and predict how firms compete on pricing, product differentiation, and advertising, as well as how consumers respond to these competitive strategies. Auction theory, a subset of game theory, examines how different auction formats influence bidding behavior and revenue outcomes, guiding the design of efficient and fair auction systems for selling goods and services. Decision-making under uncertainty is another critical area where game theory intersects with statistics and probability. By incorporating probabilistic models, game theory can assess the likelihood of various outcomes and help players make informed decisions despite incomplete information. Techniques like Bayesian game theory integrate Bayesian probability with strategic decision-making, enabling players to update their beliefs and strategies as new information becomes available. This integration is particularly relevant in scenarios like investment decisions, where players must continuously adapt to changing market conditions and new data. Mechanism design, often referred to as reverse game theory, focuses on designing rules and incentives that lead to desired outcomes, even when players act in their own self-interest. This field is essential in creating efficient markets, designing public policies, and developing protocols for decentralized systems like blockchain. By carefully structuring the incentives and information available to players, mechanism design ensures that the collective behavior aligns with societal or organizational goals. Behavioral game theory incorporates insights from psychology into traditional game theory, acknowledging that players may not always act fully rationally. It explores how cognitive biases, emotions, and social preferences influence strategic interactions. Understanding these behavioral aspects is crucial for developing more accurate models of human behavior, improving negotiation strategies, and designing interventions that promote cooperative outcomes. In practical applications, game theory and its statistical underpinnings empower organizations and individuals to make strategic choices with greater confidence and effectiveness. Businesses use game theory to anticipate competitors' moves, optimize pricing strategies, and negotiate partnerships. Governments apply it to craft policies that foster cooperation, manage conflicts, and allocate resources efficiently. In technology, AI systems utilize game theory to develop algorithms for competitive environments, such as autonomous agents negotiating in marketplaces or coordinating in multi-agent systems. The mathematical rigor of game theory, grounded in probability and optimization, ensures that its applications are both robust and adaptable to a wide range of scenarios. By modeling strategic interactions and analyzing the resulting equilibria, game theory provides a clear and structured approach to understanding and influencing complex decision-making processes. As the world becomes increasingly interconnected and competitive, the importance of game theory in shaping strategic choices cannot be overstated. It offers a lens through which to view and navigate the myriad interactions that define our economic, social, and political landscapes, enabling us to make smarter, more informed decisions that consider the intricate web of dependencies and incentives at play. Number theory and patterns. Far from being mere abstractions, number theory and the patterns it uncovers play a pivotal role in shaping our modern world, influencing everything from technology and cryptography to natural phenomena and artistic expressions. At its essence, number theory is the study of integers and their relationships. It explores fundamental concepts such as divisibility, prime numbers, greatest common divisors, and modular arithmetic. These seemingly simple ideas form the backbone of more complex theories and applications, demonstrating how pure mathematical inquiry can yield profound practical benefits. For instance, the distribution of prime numbers, which are numbers greater than 1 that have no positive divisors other than 1 in themselves, has intrigued mathematicians for centuries. Primes are not only central to number theory, but also to fields like cryptography, where they underpin the security of digital communications. One of the most fascinating aspects of number theory is the discovery of patterns and sequences within the integers. Consider the Fibonacci sequence, where each number is the sum of the two preceding ones: 0, 1, 1, 2, 3, 5, 8, 13, and so on. This sequence appears in various natural phenomena, such as the arrangement of leaves on a stem, the branching of trees, and the spirals of shells. The presence of such patterns underscores the intrinsic order that numbers can exhibit, revealing the underlying harmony between mathematics and the natural world. Modular arithmetic, another cornerstone of number theory, deals with numbers wrapping around upon reaching a certain value, the modulus. This concept is akin to the way hours cycle on a clock, resetting after 12. Modular arithmetic is indispensable in computer science, particularly in algorithms and cryptographic systems. For example, the widely used RSA encryption algorithm relies on the difficulty of factoring large composite numbers into their prime factors, a problem rooted deeply in number theory. This ensures secure communication over the Internet, safeguarding sensitive information against unauthorized access. Prime numbers themselves are a treasure trove of mathematical intrigue and practical application. The prime number theorem describes the asymptotic distribution of primes, providing insight into how primes become less frequent as numbers grow larger. Despite extensive research, many questions about primes remain unanswered, such as the famous Goldbach conjecture, which proposes that every even integer greater than 2 is the sum of two primes. These unresolved problems highlight the depth and complexity of number theory, inspiring ongoing exploration and discovery. Beyond cryptography, number theory influences various other fields. In computer science, algorithms often exploit number-theoretic principles to optimize performance and solve computational problems efficiently. Techniques like hashing, error detection, and coding theory all rely on the properties of integers and primes to ensure data integrity and rapid access. Moreover, in signal processing, number theory assists in the development of algorithms that decode and transmit information accurately, enabling technologies such as digital television, mobile phones, and internet data transfer. In the realm of physics and engineering, number theory contributes to the understanding of waveforms, vibrations, and resonance phenomena. The study of Fourier transforms, which decompose functions into their constituent frequencies, utilizes concepts from number theory to analyze and synthesize signals. This mathematical framework is essential for designing systems that require precise control and manipulation of frequencies, such as telecommunications, medical imaging, and audio engineering. Mathematical art and architecture also draw inspiration from number theory, using its patterns and structures to create aesthetically pleasing and structurally sound designs. The intricate tiling patterns found in Islamic mosaics, for example, often incorporate symmetry and number-theoretic principles to achieve both beauty and balance. Similarly, modern computational design leverages algorithms based on number theory to generate complex and innovative architectural forms that push the boundaries of traditional construction. Furthermore, number theory finds its place in biology and ecology, where it helps model population dynamics, genetic variations, and the spread of diseases. Understanding the numerical relationships and patterns within biological systems can lead to breakthroughs in predicting ecological changes, managing natural resources, and combating pandemics. The application of number-theoretic models in these areas underscores the interdisciplinary nature of mathematics and its capacity to address real-world challenges. The interplay between number theory and randomness is another area of significant interest. Concepts like random walks and probabilistic number theory explore how random processes interact with the deterministic properties of numbers. This intersection is crucial for fields like statistical mechanics, where understanding the behavior of large systems relies on both randomness and numerical structure. The ability to model and predict complex systems through this blend of randomness and number theory exemplifies the power of mathematical abstraction in solving practical problems. Educationally, number theory serves as a gateway to developing critical thinking and problem-solving skills. Its emphasis on logical reasoning, pattern recognition, and abstract thinking prepares students for advanced studies in mathematics, science, and technology. Engaging with number theory encourages a deeper appreciation for the elegance and utility of mathematics, fostering a mindset that values precision, creativity, and analytical rigor. In summary, number theory and the patterns it uncovers are far from being mere mathematical curiosities. They are integral to the fabric of our technological, scientific, and cultural advancements. From securing our digital communications and optimizing computational algorithms to inspiring artistic creations and modeling natural phenomena, the influence of number theory permeates numerous aspects of modern life. By exploring the properties and relationships of numbers, mathematicians continue to unlock new possibilities, driving innovation and shaping the world in profound and enduring ways. The birthday paradox. Ever wondered why in a room of just 23 people, there's about a 50% chance that two individuals share the same birthday? This fascinating occurrence is known as the birthday paradox, a concept in probability that defies our intuitive understanding of chance. At first glance, it might seem unlikely that in such a small group, two people would have the same birthday out of the 365 possible days in a year. However, the paradox reveals that the probability is much higher than most people expect. This counterintuitive result arises because the number of possible pairs of people increases rapidly as the group size grows. With each new person added to the room, the number of comparisons that need to be made with existing birthdays grows, significantly increasing the likelihood of a match. The birthday paradox isn't just a mathematical curiosity, it has practical applications, especially in fields like computer science and cryptography. For example, in hashing algorithms, understanding the probability of two different inputs producing the same hash value is crucial for ensuring data integrity and security. Similarly, in network security, the paradox helps in assessing the likelihood of collisions in authentication systems, which is essential for preventing unauthorized access. In everyday life, the birthday paradox highlights how our perceptions of probability can be misleading. It serves as a reminder that intuitive judgments about chance often underestimate the true likelihood of certain events, especially when multiple comparisons are involved. This insight is valuable not only in academic settings, but also in making informed decisions in various aspects of life where understanding probability is key. Moreover, the birthday paradox is an excellent educational tool for illustrating the principles of probability and combinatorics. It challenges students to think beyond straightforward scenarios and consider the complexities that arise when multiple interactions are at play. By grappling with such paradoxes, learners develop a deeper appreciation for the nuances of probability theory and its surprising outcomes. Extensions of the birthday paradox explore different probabilities and group sizes, further demonstrating the flexibility and depth of probability theory. Whether examining the likelihood of three people sharing a birthday or calculating the probability of any pair matching in larger groups, these variations provide additional layers of understanding and showcase the broad applicability of the paradox. In essence, the birthday paradox underscores the importance of statistical thinking in uncovering truths that aren't immediately apparent. It bridges the gap between abstract mathematical concepts and real-world applications, illustrating how probability can reveal hidden patterns and inform our understanding of seemingly simple phenomena. By embracing the insights offered by the birthday paradox, we gain a more accurate and comprehensive view of how probability operates in various contexts, enhancing both our theoretical knowledge and practical decision-making skills. Benford's Law. Benford's Law is a fascinating statistical phenomenon that reveals a surprising pattern in the distribution of first digits across many naturally occurring datasets. Unlike what our intuition might suggest, the number 1 appears as the leading digit much more frequently than higher digits like 9. This non-uniform distribution challenges the assumption that first digits are random and uniform, offering intriguing insights into the underlying processes that generate numerical data in the real world. At its core, Benford's Law states that in many naturally occurring collections of numbers, the leading digit D is an element of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, occurs with a probability proportional to log base 10 of 1 plus 1 over D. This means that smaller digits appear as the first digit more often than larger ones. For example, about 30% of the time, the first digit is 1, while only about 5% of the time it is 9. This pattern holds true across a wide range of data sets, including financial records, population numbers, physical constants, and even the lengths of rivers. One of the reasons Benford's Law emerges so frequently is its scale invariance property. Whether you measure something in meters, kilometers, or miles, the distribution of first digits remains consistent. This characteristic makes Benford's Law particularly useful in various applications, such as fraud detection in accounting and auditing. By analyzing financial statements, auditors can identify irregularities or manipulations if the distribution of first digits significantly deviates from what Benford's Law predicts. Similarly, election data, tax returns, and scientific data are often scrutinized using this law to ensure their authenticity and accuracy. Another intriguing aspect of Benford's Law is its relationship with logarithmic distributions and exponential growth. Many real-world processes that involve multiplicative factors, such as population growth, stock prices, and natural phenomena, naturally align with the patterns predicted by Benford's Law. This alignment arises because these processes often span several orders of magnitude, allowing smaller numbers to dominate the distribution of first digits. Benford's Law also extends beyond first digits to second and subsequent digits, though the deviations become less pronounced. The law provides a comprehensive framework for understanding how numbers are distributed in various contexts, offering a window into the mathematical structures that govern natural and social phenomena. In the digital age, the applications of Benford's Law have expanded with the advent of big data and advanced computational tools. Data scientists and analysts leverage this law to validate large data sets, ensuring their integrity and uncovering hidden patterns. For instance, in forensic accounting, deviations from Benford's distribution can signal fraudulent activities, prompting further investigation. In scientific research, adherence to Benford's Law can validate the credibility of experimental data, while significant deviations might indicate errors or biases in data collection. Educationally, Benford's Law serves as a powerful tool for teaching concepts related to probability, statistics, and data analysis. It illustrates how mathematical principles can uncover hidden truths in seemingly random data, fostering a deeper appreciation for the interplay between theory and real-world applications. By exploring Benford's Law, students and researchers alike gain valuable insights into the nature of numerical data and the importance of statistical patterns in various disciplines. Moreover, Benford's Law has intriguing philosophical implications about the nature of numbers and their occurrence in the universe. It challenges us to reconsider our perceptions of randomness and order, highlighting the underlying mathematical harmony that often goes unnoticed in everyday life. This realization underscores the profound interconnectedness between mathematics and the natural world, revealing how simple numerical rules can govern complex systems and phenomena. In summary, Benford's law demystifies the seemingly random distribution of first digits in many datasets, unveiling a consistent and predictable pattern that has significant practical and theoretical implications. From enhancing the accuracy of financial audits to validating scientific research, the law provides a robust tool for analyzing and interpreting numerical data. Its widespread applicability and underlying mathematical elegance make Benford's law a cornerstone in the study of statistics, offering profound insights into the patterns that shape our world. How casinos use statistics against you. You're at the roulette table, watching the wheel spin and the ball dance around the colorful compartments. As you place your bets, you might feel a rush of excitement, hoping luck is on your side. But behind the scenes, casinos are meticulously applying statistical principles to ensure that the house always maintains an edge over players. This sophisticated use of mathematics is the backbone of the gambling industry, allowing casinos to predict outcomes, manage risks, and maximize their profitability. At the heart of casino operations lies the concept of probability. Every game offered by a casino, whether it's roulette, blackjack, slots, or poker, is designed with specific probabilities that favor the house. In roulette, for instance, the presence of a single or double zero increases the number of possible outcomes beyond the standard 36 numbers. This slight adjustment shifts the odds in favor of the casino, ensuring that over time the house consistently profits from the game. Casinos employ the law of large numbers, a fundamental statistical principle, to their advantage. This law states that as the number of trials increases, the actual ratio of outcomes will converge on the theoretical probability. For casinos, this means that while individual players may experience wins and losses, the overall results will align with the house edge when thousands or millions of bets are placed. This statistical reliability allows casinos to forecast their earnings accurately and maintain stable operations. Another critical aspect is the use of expected value, which represents the average outcome of a bet if it were to be repeated many times. Casinos calculate the expected value for each game to determine how much they can expect to earn from each bet placed. For example, in blackjack, the specific rules regarding the number of decks used, payout ratios for blackjacks, and dealer behaviors are all calibrated to ensure that the expected value remains in the casino's favor. This meticulous calculation ensures that the house edge is preserved across different games and variations. Moreover, casinos utilize combinatorics to understand and exploit the myriad possible combinations of game outcomes. In poker, for instance, the number of possible hand combinations is vast, allowing casinos to design games that are both engaging for players and profitable for the house. By analyzing these combinations, casinos can set rules and payouts that maximize their returns while still providing players with a fair chance of winning, keeping the games attractive and competitive. Risk management is another area where statistics play a pivotal role. Casinos must balance the potential rewards they offer to players with the risks they incur. By analyzing historical data and player behavior, casinos can adjust betting limits, modify game rules, and implement strategies like card-counting countermeasures in blackjack to mitigate risks. This proactive approach ensures that the casino remains profitable even during periods of high player activity or unexpected shifts in game popularity. Furthermore, data analytics and predictive modeling have become indispensable tools for modern casinos. By collecting and analyzing vast amounts of data on player behavior, betting patterns, and game outcomes, casinos can make informed decisions about game offerings, marketing strategies, and operational adjustments. For instance, slot machine placements are often optimized based on statistical analyses of player flow and engagement, ensuring that high-revenue machines are strategically positioned to attract the most attention. Casinos also leverage statistics in their marketing and loyalty programs. By analyzing player data, casinos can identify trends and preferences, allowing them to tailor promotions and rewards that encourage continued patronage. This data-driven approach not only enhances the player experience, but also fosters customer loyalty, contributing to the casino's long-term success. The psychological aspect of gambling is also intertwined with statistical strategies. Casinos understand that players are more likely to engage and continue playing when they perceive fairness and excitement. By designing games with appealing odds and incorporating elements like near-miss outcomes, casinos keep players invested and motivated to keep betting. This subtle manipulation of perception, grounded in statistical knowledge, enhances the overall profitability of the casino. In essence, the math behind gambling is a sophisticated blend of probability, statistics, and data analysis that ensures casinos remain profitable while offering engaging and seemingly fair games to players. By carefully designing games with a built-in house edge, managing risks through statistical modeling, and leveraging data to optimize operations, casinos effectively use statistics to maintain their dominance in the gambling industry. While players may enjoy the thrill of the game, it's the behind-the-scenes application of statistical principles that truly drives the success and sustainability of casinos worldwide.